Hello everyone. So in this video, I'm going to give you a very brief discussion of electrodynamics inside matter. Okay. So far we have discussed a lot about electrodynamics in vacuum, where of course there can be charges which are moving around or dancing around along with the electric fields. Essentially, that whole phenomena was assumed to be taking place in vacuum. Okay. For instance, if we are looking at electrodynamics in, let's say, air or water, the situation gets slightly more complicated. Okay. So, for air, because it's a very rare medium, I mean, one can probably vacuum electrodynamics is probably a very good approximation, but again, I mean, there are situations where it becomes important to treat air as a dielectric. So there are certain phenomena, as we'll see, that happens, which are different from, which are special to what would happen inside matter. Okay, so for that we need to somehow develop a theory inside matter. So now, as you know, inside matter there are many atoms and molecules, and there are atoms, and these atoms have charges. They have electrons, they have nucleus, and the whole situation is very complicated if we want to solve the electrodynamic equations inside matter. Okay, because the matter is itself very complicated at the microscopic level. What we intend to do, therefore, is to develop an effective theory which is valid at length scales which are large compared to the size of an atom. Okay, so if we are able to develop some kind of an effective theory, then we can just deal with that effective theory and find solutions, and then we'll be able to make predictions of electrodynamics inside matter. So, of course, the microscopic electrodynamics that we have described so far, or the vacuum electrodynamics that we have described so far, is completely valid inside matter as well. It's not that it's breaking down. What is happening is the microscopic picture is very complicated to give a proper description or keep track of all the charges. So we need to develop some kind of an effective description of electrodynamics, which is valid at longer length scales, and therefore what we are going to develop now is called macroscopic electrodynamics. Okay, so what I have in mind is, let's say you have many matter molecules. Okay, so let's say or atoms, you can say. There are many matter atoms which are which are present inside matter, and let's say what I have shown here are the the electron clouds, and then there is a a positive charge nucleus in all these cases. And basically, when you have an electric and magnetic field, they can influence these charges, and they can, these charges can then themselves create their own electric field and magnetic field. Okay, so again, for this discussion we are going to restrict to materials which are called dielectrics, and these are essentially material where you don't have free electrons moving around like conductors. Okay, here you have atoms like this where the electrons are bound to the atoms, and of course what can happen is the center of the negative charges due to the electrons may not coincide with the positive charge of the nucleus, and therefore there can be dipole moments, etc. But effectively, the electrons are not free to move around. Okay, so in this sense, these dielectrics are essentially insulators, and what we're going to try to understand is how to incorporate the effect of these charges that are bound to the atoms or the constituents. Okay. And as I was telling you, we are going to try to develop a theory which is a macroscopic theory, So this macroscopic theory is also going to be local, as we'll see that, it's going to be a local description again. But this local theory, when we say a point here, what we would mean is a very large region. Okay, as I said, the length scales of the validity of this theory is going to be large compared to the size of the atoms, and there can be many atoms within the size of a point, if you like. Okay, for which we are going to give the description. Okay, so if I consider a region like that, okay, it's this is going to be our point, if you like, this circle, and then there would be it's possible that there are lots of like charges and several things happening inside, but so everything would be averaged to some kind of an electric field, which will be pointing inside some direction inside inside this region, and this is what I'm going to refer to as my effective or macroscopic electric field. Okay, let's say this is going to be my macroscopic electric field or magnetic field. Okay, so the EM fields are macroscopic in this sense that it's basically an averaged electric field. So all the effects, all the complicated effects are averaged out over a small tiny region, and then we will call that tiny region point, and then try to develop a theory, a local theory of that scenario. Okay, so this is the thing that we have in mind when we talk about dielectrics, and it turns out that this particular effective theory turns out to be very similar to the electrodynamics that we have talked about so far. Okay, it's just a very tiny modification or very simple modification with which we can describe electrodynamics inside matter very comfortably with the knowledge that we have gained so far. Okay, so of course, there are materials which are more complicated and things can happen, but those are special materials. But most of the dielectrics, the description of electrodynamics inside the effective theory turns out to be simple, and we are going to here describe or focus on only that simple theory, just to give you an idea of what goes on inside matter. So as I said, so let's first talk about the electric fields inside matter. And in this first description, let us think that the electric fields are static. On an average, they are static. Of course, there are fluctuations at tiny length scales, but on an average, they are static over a distance which is large compared to the size of the atom. And so in that case, what we are going to find is, if we consider a single atom, let's say, okay, and let's say we consider a single atom, so basically, this is the electron cloud. Okay, again, this is very quantum, but this description of the atom is quantum. But again, we are going to do some, kind of a classical modeling of the atom and try to deal with it accordingly. Okay, we are going to give a very simplistic description. So, so let's say there's some electron cloud and there's some positive charge of the atom, and the macroscopic electric field in the region where this atom is located, let's say that is pointed in some direction, let's say in this direction. Okay. So what this macroscopic electric field is going to do, it is going to polarize the atom. That means, it is going to separate the positive charge center and the negative charge center, and thereby produce, convert the atom into a dipole. Okay. So, so this is what is going to happen. I mean, so you are going to so we are going to observe that because of this electric field, without the electric field, there is more or less the centers of the charges, plus and minus, they more or less coincide. But in the presence of the electric field, the plus charge is going to shift, and the minus charge is going to, the center would be somewhere around here, so that there is an effective dipole moment. So this is the scenario where I have produced an electric field. So this is without electric field, and this is the case where I have an electric field, and therefore there is going to be a dipole which is pointed from the negative charge to the positive charge. This is small p. Okay, I hope you can distinguish between my small p and capital P. So this is small p. This is the dipole moment that is generated in an individual atom due to the existing averaged electric field at the location of the atom. Okay, so this is very important. This averaged electric field has all sorts of effect. It takes into account all sorts of charges, and we actually don't have to perform that sum over all these charges or keep track of all these things if we are giving this effective description in this way. Okay, so if this is the average macroscopic electric field. So this is, if you like, the macroscopic electric field. Okay, so that produces this polarization, and in various modeling of the atom, okay, you will find that this polarization is going to be proportional to the amount of macroscopic electric field at that location. Okay, so again, later on in this video, I will try to describe to you a very simple model and show this to you, exhibit to you. But like this here. So therefore, we can say that this polarization of the atom or the dipole moment. So P is the dipole moment. Okay, so this is the dipole moment, and so the dipole moment that develops is basically proportional to the electric field, and I have called the proportionality alpha. Again, this alpha can in general be a tensor, it can have directional dependencies, etc. But in this brief discussion, we are going to keep life simple, and we are going to say that it is directly proportional to alpha. Okay, alpha is just one number, and the dipole moment is proportional to the electric field. Okay, so under such, again, this is going to be a valid assumption for many material. Okay, it's going to lead us to very reasonable theory and very reasonable expectations. So this is again something. This is, if you like, a modeling. Okay, so so now, if you consider such a situation, then every individual atom develops this dipole moment in the presence of this electric field. This electric field, I'm assuming that it is a static electric field at the moment. Okay, it is independent of time. Okay, so of course the atoms can also have higher multiple moments. Particularly like if it is a complicated atom, or if you are thinking about molecules, you're talking about so large length scales that they are large compared to even the molecules. So in that case, they can have a higher order multiple moments, but again, the effect of those moments are, as you know, they die off very quickly in terms of distance, and therefore we are going to ignore all those higher order multiple moments, and that assumption again is a very good assumption for most material. Okay, so we are going to ignore the higher multiple moments and just focus on the dipole moment that is developed due to this macroscopic electric field at a particular point. Okay, so with this, every atom develops the dipole moment. Now you can ask that over this whole region, where there were lots of atoms in some sense. Okay, so there, can we say that, what is the average dipole moment that has developed over this macroscopic region that we are considering? Okay, so if the number density of the atoms or whatever the constituents are, if the number density of that is n, then all I have to do is to find the average dipole moment per unit volume, I have to multiply the dipole moment of an individual atom with the number density of the atoms, okay, in that region. So if I do that, then this is the combination that is going to give me what I would call polarization. Okay, again, this is an effective macroscopic field. The polarization is also a field. It can differ from point to point, but it is, that point, as I was trying to explain, is large, and that contains a lot of atoms, and in general, okay, and that therefore this takes into account some kind of an averaged effect. Okay, so all our discussions here are going to be averaged effect about macroscopic electric field, macroscopic magnetic field. Okay, so that is the main idea of writing down an effective theory. Okay, we are talking about larger length scales. Okay, and the word macroscopic refers to this larger length scale thing that we are doing. Okay, so if the individual dipole moments are proportional to the electric field, so you can expect that this averaged polarization, this is also proportional to the electric field at that point. Okay, again, this is the averaged macroscopic electric field, average total macroscopic electric field at a particular point like this. Okay, that I was describing here. Okay. So then if it is proportional to that, then that proportionality constant by convention is written in this way. It's epsilon naught, which is the permittivity of vacuum, multiplied by another constant, which is called the electric susceptibility. Okay, but this thing again can also be a tensor, but I'm not, it can be a 3 tensor, but I'm ignoring, such complications at the moment. Okay, I'm just considering only one value for this, it's like a number. Okay, let's say. Okay. So in this, if this is the case, then it's very clear. Then you see, chi times E would be n times alpha, which is the alpha is the polarizability of a single atom. Okay, it tells us that to the degree of dipole moment that is generated when you have a macroscopic electric field over the atom. Okay, so. Yeah. So this, if you again, just to emphasize this point, this macroscopic electric field is due to all the charges that exist here. Okay, everything taken together, averaged, and then there is some macroscopic electric field. Okay. So and these are, there can be actually some other kind of free charges here also, some kind of impurities inside matter, etc. And those are also contributing to the macroscopic electric field, and everything here is contributing to the macroscopic electric field. It's just an effective electric field. Okay, this is a very important point, and I wanted to appreciate that. Okay, so now we are in business. If we do that, we know that the scalar potential due to one particular dipole is given by this expression, right? The scalar potential is given by this expression. This we have seen before in the multipole expansion. And so now, if we want to convert this into a dipole moment density, okay, then all I do is to basically convert this into a volume integral, and essentially, this volume integral is taking, sum over all the little atomic dipoles that are contributing to this scalar field at that particular point. Okay, so this if I do this integration, then if I write it in this integral way, then the first thing that I note is I can take this part and write it as the gradient of this quantity 1 by r minus x. Okay, so this I can immediately write. Okay, so if I write this, then I can perform the usual kind of procedure. I can take this derivative and write it as a total derivative like this. Okay, this one is the divergence of this vector, and then I have to take away the term where this derivative hits only the p. Okay, that term needs to be taken away because that term is not there in this original expression. But when the derivative hits the denominator, then we have this gradient and p dot gradient, that term is there. So I have to subtract away this additional term which comes in when I take the derivative outside. Okay, so then this is just an identity. Okay, this is just equal to this, it's just an identity. But once I write it in this form, you see, then this total derivative can become a surface integral now. And this thing remains as a volume integral like this. Okay, so once I have written in this way, then it is very fascinating. You see, if you don't look at this term again, we have been not looking at boundary terms so far. But when you are talking about a dielectric slab, or let's say a glass or water or something, that can have a boundary. Okay, so here boundaries are occur naturally for medium like this. And therefore, this term also, is very much physical, and, it's important to discuss terms like this as well. Okay, there can be interfaces between two media, etc., etc. Okay, so this kind of boundaries can be very important here. So I've kept this term here. But if I look at this term, it is very clear that, you see, this term is such a term where you can interpret the numerator as some kind of a charge density, which is creating this potential here. Okay. Again, P is some average quantity which is creating this potential at that point R, but this you can think of as some kind of a charge density. So there is some charge density which is creating this, and because it is created because of some bound charges, the charges are bound to the atoms, they cannot move around. Therefore, I'm going to call them bound charges, okay? And therefore, the charge density, this effective charge density in terms of the polarization that I'm going to write, I'm going to call bound charge density, okay? Now, as far as this surface integral is concerned, this P is concerned, this also can be considered as a charge density, but it's a surface charge density. Okay, I mean the effect that produces this is also very obvious. Let's say you have some kind of dielectric like this, some kind of dielectric slabs where you have atoms like this, and let's say in these atoms there has been some kind of a polarization because of some applied or maybe it is applied or even some because of some effects, there are polarization here. So if the polarization happens like this, okay, let's say there's some electric field which is in this direction, which has resulted in this polarization, then as you can see, the plus charges are moved on the right hand side and the minus charges on the left hand side. So this boundary this boundary would develop minus charges like this. Okay, and this boundary would develop plus charges, an effective charge, surface charge density. This particular surface charge density is what I am referring to as this P dot n, this thing. Okay, so that is going to be there, and that is going to be interpreted as the surface charge density, this boundary term. Okay, and this is happening precisely because of the fact that there is this dipole moment for individual atoms. Okay. So therefore, this is a nice description for that now. So we have effectively reduced, we identified, we have given the description in terms of polarization, which is basically average dipole moment per unit volume. And that object can be used to quantify a bound charge density and a corresponding surface charge density. Okay. So now this bound charge density is something which is important and interesting because it is present in the bulk of the material. And we're going to try to write down an electrodynamic theory in the bulk of the material. So you are going to focus on the bound charge densities that exist inside the material. Okay. So now with this in mind, if we just turn back to Gauss law, okay, let us turn our attention to Gauss law. So Gauss law tells us that the divergence of the electric field, again the divergence of the macroscopic electric field in this case, would be given by this this is the charge density. This is the total charge density. Okay, now the total charge density obviously comprises of these bound charges that are there, or these effective charges that are produced because of this dipole moment. Okay, so therefore I split up the total charge into such bound charges plus some free charges. As I said, inside the matter there can be free charges moving around, and that can essentially source the Maxwell's equations as well, or source the electric and magnetic fields. So those you have to keep some room for those free charges as well. Okay, you can have some impurities, or you can put in one charge and try to study it, etc., etc. Okay, so therefore this this phenomenon you have to keep these free charges separately, and write the bound charges separately. Now once you do that, then you see we have I've tried to argue that this bound charge can be written as the divergence of the polarization. If I write it as a divergence of the polarization, then I can take it on this side of the equation and combine the electric field and the polarization into something called a electric displacement vector. Okay, so this one is denoted as a D, and if I write this as some effect, again this is also an effective field, okay, macroscopic field. So this, in terms of this D, our Gauss law takes again a very simple form. It's the divergence of D equal to some source, which is this free charges. Note, this epsilon has gone into, this epsilon has gone and multiplied this electric field. It's a constant. It's so I can take it inside the integral and write it in this form. So you see, Gauss law description inside matter, it's not terrible. It's just that you talk about the D instead of the E, and this D essentially it's basically E plus some contribution that comes out of the bound charges. Okay, I mean, isn't that nice? That now this is our effective Gauss law inside matter. Okay, so that's something. Now, as you can see, going back to our previous point, that this polarization this object can, I was trying to argue that it should be proportional to the macroscopic electric field at that point. Okay, whatever that is. Okay, again, this is a local, this is a function of, space and time. Time dependence I'll discuss a little bit later, but this is a function of space. So it's it can differ point by point, but at every point, the polarization is proportional to the electric field in most reasonable models. This is what is the case, and it's also something which is observed. Okay, so in this case, this is epsilon times chi times E. Again going back to this is just equal to this, and then if I rearrange, then I can write the D also becomes proportional to the electric field. Okay, in this particular case, for a material for which this polarization can be modeled in this way, that it is proportional to the macroscopic electric field, then D also becomes proportional to the electric field, and this proportionality constant is called the permittivity of the material that we are talking about, or the dielectric that we are talking about. Okay, and this therefore is given as denoted by a single notation. It's called epsilon. Okay, so basically this is what we conclude, that this new D vector is also proportional to the E vector. There's just this epsilon here, and then there is this Gauss law modified, which says that now we should talk about the divergence of D equal to the free charges that are there, and we can forget about the bound charges entirely. Okay, we can just try to solve this equation and know what is D, and if this relation is also valid along with it, then if I know what is D, then I know what is E, because I just have to divide by a constant epsilon. Okay. So isn't that beautiful? Like, it's already very nice. So now, as I was telling you, so if this is valid, okay, again, there are materials for which this is not valid, but if this is valid, then I can take it and plug it back into Gauss law, and then I can write it in this form, where I'm talking about the macroscopic electric field now. I'm not talking about any displacement vector. I'm talking about the electric field, and the macroscopic electric field then is given by the free charges divided by epsilon. So the Gauss law is essentially, modified by this small constant here. Earlier it was epsilon naught, but now it is epsilon, where epsilon naught and epsilon are related by this equation here. Okay. Okay, very good. So that was the story about the electric field. What about the magnetic field? So for the magnetic field, we play a very similar game. Okay, again, for the magnetic field, there are also some quantum effects that come in let's say, the electrons have angular momentum, they have spin, these are all, if I treat them like quantum mechanically, then if the effect of that, so the essence of that is to give these atoms or these constituents some kind of a average magnetic moment. Okay, so this is the average magnetic moment that can develop in individual atoms. So again, the picture is very similar to the previous picture. Let's say you had some atoms, but now of course there are charges inside also. Of course there are charges inside. Some plus charge, like this, that are there. Okay. Again, for now I'm considering, let's say static magnetic fields for a moment. And then these individual objects can also, because of these effects of angular momentum and spin, let's say of the electrons, or even for the nucleus, they develop some kind of an effective, let's say, magnetic moment. Every one of them, they develop some effective magnetic moment, which I'm denoting by some arrow. Okay, and if you have some macroscopic magnetic field here, okay. This is again some macroscopic magnetic field, just like the electric field. Then these tend to get aligned along the magnetic field, and they in turn produce some kind of magnet. So the magnetic field is a total magnetic field that is produced due to all these effects. There's some total magnetic field that is produced, and so the individual atoms, they have this magnetic moment, which is m. Okay, which I'm denoting by m. Okay, so essentially. Now I can go ahead. Now I can go ahead and define my magnetic moment. I can go ahead and define my magnetic moment per unit volume, again in the same way that I did how I did define polarization. I can multiply it by the number density of the atoms, or the constituents, whatever they are. that number density, if I multiply with the magnetic moment of the individual constituents, then I will get something which is the average magnetic moment per unit volume. Okay. Again, this quantity is very similar in spirit to the polarization, and it is known as the magnetization. Okay, very good. So with that in mind, again, we are going to, in simple modeling of matter, of dielectric matter, then we would say that this magnetization is basically proportional to this magnetic electric field. The magnetization is proportional to the magnetic field, and this proportionality constant we are going to write in a very weird way, and that is written in a very weird way because of historical reasons. Also, there's a nice reason why you'll soon see. There's some nice bit of algebra that works out. But this is written, this proportionality constant. I could have written some chi tilde here, chi m tilde here. That I could have done, but it's written in this way. You'll see, soon why, that is more algebraically slightly convenient. But mostly, this has been done because of historical reasons. Again, the bottom line is same, that if I have some macroscopic electric field, then more or less, these tiny magnetic dipoles, they kind of align, and their effect, their averaged effect would be in a direction which is in the direction of the magnetic field, and therefore the magnetization is in the direction of the magnetic field. Okay, right. So once I define it in this way, then again there are some very interesting classifications of various material. Okay, where this chi m is called the magnetic susceptibility, and depending on what the value of chi m is, if it lies between -1 0, these are called diamagnetism, or that phenomenon is called diamagnetism. And then if it is greater than 0, it's a paramagnetic material. And if the magnetization is non-zero even when this B is 0, such materials are called ferromagnetic, and these are all very interesting material. I can spend a lot of time on them, but again, I'm not going to, because we are almost running out of time. This is not something I'm going to spend much time on. It's just this modeling that I'm going to keep in mind, that our magnetization is proportional to the magnetic field. That's the effect, or that's the essence that we want to carry ahead. Again, this quantity, again, to emphasize, this quantity can again be a in general a tensor, but again, we are ignoring such effects of directional dependence, etc. Okay. So very good. So now, if we define it in this way, then again we are going to do a very similar exercise as we did before. So the vector potential due to a magnetic moment. Okay, an individual magnetic moment m. Okay, this takes this form. Okay, I mean, we have done this again, in great detail when we did magnetostatics. So now. I can convert it into an integral over the magnetization, which is the magnetic moment per unit volume, and then integrate it over the volume. Okay, again, this field, this magnetization field that is being produced, again, I'm considering to be a magnetic field, macroscopic field, but again, it is defined like a field at every point in space-time. It's just that what I'm calling point is a big size object, containing many atoms, and some averaged effect there, is giving rise to this M. Okay. So that's what I have in mind. Okay, so very good. So this M is there. And now again, we are going to do some algebraic manipulation. So this object here, again, we are going to write as the gradient of some quantity. So this is basically magnetization cross the gradient of this quantity. Okay. Now, if it is the gradient of this quantity, then again, I can use an identity and write this as the curl of this object inside, and the curl of the magnetization divided by this, r minus x. Okay, this distance. Okay, again, r is the point where I'm trying to find the averaged vector potential, and this magnetization from various points can have contribution there, and therefore it is an integral over the whole volume of the material that I'm considering. Again, if you go from here to here, this identity you can just check, here I have checked. So if you take the curl of m times some scalar phi, okay, this scalar, I'm considering to be, whatever this is. Okay, this is the scalar phi. This is what I'm calling phi here, in here. And then if you take the curl, then if you write it in terms of epsilon ijk, then you will see there are two terms. Again, these two terms, if you rearrange, then you can write it in this form. And once you write it in this form, you see that minus of this object, okay, right. Am I missing a sign here? Right. Let me just check. So epsilon ijk j m phi and right. So I guess I'm missing a sign here. So ijk. Please check this once. I think I'm missing a sign here. So that's del j mk, and so this is del j mk times phi and mk del j times phi. So this jk, this becomes the curl of m. That's correct, and this one becomes the right. This one becomes comes with a minus sign. That's right. Yeah. So this one comes with a minus sign. Yeah. So I guess if I want to express this one comes with a minus sign because epsilon ijk. Let me check this. So right, this is correct, and this is epsilon ijk mk. So here I have a sorry about this. So here I have this thing. So if I take the curl of this object, then this is the ijk del j mk phi, and then I have epsilon ijk del j mk. That is correct, where the derivative acts on this mk, and phi is there, and then I have mk. Which is mk del j phi, right? So this object here, I have switched the k and j, that's why I've got the sign. And if I've switched the k and j, I have got the sign. So this object can be written in this way. And indeed, what I observe, this m cross grad phi is equal to curl of m times phi minus curl of m phi. Okay, so I'm missing a minus sign here. I'm sorry, in this term I'm missing a minus sign, and so if I'm missing a minus sign, then I guess so am I missing a minus sign? Yeah. Sorry, in this term I'm missing a minus sign. Yeah, in this term I'm missing a minus sign, and sorry, in this term I'm missing a minus sign, and here again, I can use this corollary of the divergence theorem, and I can write it as a surface term, and now I think the sign gets corrected. Okay. So, so otherwise, you would have written down this on this side, cross this. Okay. So, so basically, right. Am I right about that? The derivative that you use. Yeah, okay. Yeah, maybe I'm also missing a sign here. Okay, one can check this against standard textbooks. But I think I'm also missing a sign here. And if I miss a sign here, so this is written in this way. Okay, this is a sign. There's a sign. This sign is there. Okay, this sign is there. And and if I write this sign here like this, then basically I will have, please check this once, and then this is basically my, this is basically, again, I can interpret this. So this algebraic, by this algebraic operation, again going back, this object I have written as one total derivative and one, this object here. So again, this expression comes from this term here, okay, and right. So this sign is, there is a sign off. So this is minus. So if this is minus, then I can now say that I can interpret. Now I can see that, you see, this is the, I can interpret this as some kind of a current density. Okay, this is the volume integral. This is the leftover volume integral. So this I can interpret as some kind of a current density, and this current density, is what I have interpreted as some kind of a bulk current density. It's a bound current density because these are, again, magnetization is happening, which are bound to these atoms or whatever the constituents are. So that is giving rise to this kind of a bound charge, bound current density. Okay, and here this one again I'm going to interpret as a bound surface current density. Okay, and this surface current density should be n, it's minus n hat cross, n hat is this normal vector to this surface, so it's minus n hat cross m. So that I am writing as m cross n hat. So this result is correct. Okay, as written. Okay, so very good. So yeah, I just messed up with this, with one of the signs here. So so essentially what I now have in mind is, you see that there are these tiny currents that are giving rise to, let's say, there are these tiny currents that are giving rise to, let's say, my my bound current. Okay, there are these currents. Okay, this is some effective current that I am writing down. Okay, you see, the origin of this is, the spins and the angular momentums. Maybe the origin is quantum mechanical, but I'm trying to model that, all those effects into some kind of currents like this. And if we have this and there is a non-trivial boundary, then as you can see from here, that because of these currents, there can be a non-trivial surface current that is flowing through the surface like this. Okay, through the boundary. Okay, so this surface current is what I'm denoting by, this Kb. And then there's a bulk current effectively, which I'm writing it down in this way. Okay, so very good. So if I do that, then now let's look at Ampere's law. Again, this is in the magnetostatic case. Okay, if I look at Ampere's law, then this total, current density, okay, that I can again split. Okay, this is very essential to remember. Now in this description I am giving some average macroscopic effect, but this average macroscopic effect is derived from the original Maxwell's equation. Okay, so the original Maxwell's equations are valid, but it's too complicated. So what I do is I average the original Maxwell's equation, and once I average it, okay, over some long distances, then this averaged current, this can be written in two ways. One is this contribution from this, from these little magnetic moments. Sorry, this little magnetic moments. This is what I'm calling the bound current. Okay, inside the bulk of the material. And then there can be free currents as well. Okay, inside the bulk of the material, there can be, some freely flowing charge which you want to keep track, and these are responsible for those free currents. Okay, it's the same kind of thing that we did just before. So now, once we do this, then it is again now very clear what to do. Then I can take this bound current. Sorry, I can take this bound current and write it as the curl of m, because that is what I have argued here. Just by looking at the expression of the vector potential, I could argue that curl of m has an effect of having a effective current. Okay, curl of the magnetization. So if I write it as a curl of the magnetization, then I can take this and I can bring it on this side of the equation, and then take this combination and call it an H. This is some H vector. Okay. And you will see many books say that this is the magnetic field instead of this, and treat this as a more fundamental object because of this instead of this B. But it is not true. Okay, I mean, this is some effective object. Okay, it is some effective object, and because people have been dealing with matter and material, so perhaps historically, this came to scientists, or physicists more naturally than the original magnetic field. Okay. So therefore, but this is, some kind of a macroscopic object. That is how we are going to approach it in the modern way. That this is some macroscopic object, and once I write the object as this combination of the magnetic field and magnetization, then this H is essentially, in terms of the H, the Maxwell's equation again takes the same form as the vacuum Maxwell's equation. The curl of H equal to the free currents. Again, you see the epsilon has disappeared from here and it has gone here. Okay, sorry, the mu naught has disappeared from here and has gone here. Okay, so again, if I now assume that previous form of magnetization proportional to the magnetic field, then I can just combine it here, do some algebra, and write it in the form 1 by mu naught 1 plus chi. Again, this chi m was called the magnetic susceptibility. Okay, so this this combination therefore is H is equal to the magnetic field, and the proportionality constant instead of the numerator now sits in the denominator, and in the same way as it happened for the electric field, if you remember. Okay, so this combined thing is known as the magnetic permeability of the medium or the material that we are talking about. Okay, and in many cases, many dielectrics of interest, this mu naught is a constant. In fact, it is very close to mu naught. Okay, this mu is a constant and it is very close to mu naught. Okay, for most materials. Okay, for most dielectrics, that is very common. For most common dielectrics, this is very close to mu naught. Okay, so therefore, this thing that we have. This effective theory that we have, the effective magnetic field, I can just write as some constant times H. And if I do that again here, then I can rewrite the same Maxwell's equation, this effective Maxwell's equation, or the macroscopic Maxwell equation, Ampere's law. Okay, that I can write in terms of curl of B equal to mu times J. Again, you see, the whole effect of matter just goes into modifying this one particular constant. That's the beauty of treating or writing down some effective theory in this way. We don't have to care about the microscopic currents and the microscopic charges. They are all taken into account effectively in this way, and we don't have to talk. We can now go ahead and solve this equation, and we'll get the macroscopic magnetic field and the electric field. Okay. So again, these two situations I was talking about about the static case. Okay. So I should again emphasize, as I've written here, that this B, or the effective magnetic field, is in some sense more fundamental than the H. Okay, that's at least my point of view. I mean, several people take various points of view, but that is effectively my point of view. And you will see many books, what it does, even in vacuum, they take the B and divide it by the mu naught and then write down some H. You see, in vacuum, this chi m, that part, if you like, this part is just 0. So then, we just have mu naught. And then they define an H by dividing the B with the mu naught. And then they talk about the H, and then they call it the magnetic field. Okay, but again, our H appears only inside matter, and it appears because we have to perform this combination of magnetic field and the magnetization. Okay, that's our, at least that's my notation, and that's how I think about it. Okay, and I also think that this is a very convenient way to think about it. Okay, so now let's look at the macroscopic Maxwell's equation, where you have also, some time-dependent electric field, and time-dependent, bound charges are also time-dependent. Okay, so if the bound charges are time-dependent, of course, there are free charges that can be time-dependent, etc. There's a free current, and the free current and the free charges themselves satisfy a conservation equation, while the bound currents and the bound charges, they also satisfy a conservation equation like this. Okay, again, this is some effective conservation equation that had to be satisfied if our effective Maxwell's equation had to be consistent. You know that this conservation equation just follows from an effective manipulation of the Maxwell's equation. Okay, so this kind of thing had to be true if let's say for the free charges, it's kind of intuitively obvious. The free charges are moving around, that's creating a current, and charge is not getting created or destroyed, so it's obvious that that free charge will be conserved. But then now if you take the total charge, which is a combination of the free charge and the bound charges, and if you take the free charge effect away, then of course the bound charges, the way I'm writing down in the effective way, the effective Maxwell's equation, for that the conservation equation must be valid, and this is what I'm going to use for when there is a time dependent case. So the bound charge, again, I can write in terms of the polarization as the divergence of P, and that divergence I can combine with the divergence of J, and come up with this quantity whose divergence is 0. Okay, so again, going back here in this way of formulating, you see, if the curl of H is equal to JF and this curl of B equal to mu times J, then obviously it is true that that now if I take a divergence of this, the divergence of the free current, that's going to vanish. Okay, it's basically part of this magnetostatic ansatz. Okay, but now we are going to say that we are moving away from static, this kind of static ansatz, and so even the bound current that is written as the curl of M. So if it is written as the curl of M, then that part is basically that kind of current for the static case. Or the magnetostatic case, that kind of current must also have a vanishing divergence. Okay, but now here we are going to say that things are time dependent, and the bound charges can also be time dependent. Let's say you have applied some time dependent electric field. Let's say some electromagnetic wave is going through matter. Then the bound charges can also have some time dependence, right? So then this manipulation is right, and then this effect of the bound charges is essentially taken away. The effect of the time-dependent bound charges, or the time-dependent motion of the bound charges, is taken away, and this quantity can now be thought of as that curl of M. Okay, the thing that we discussed earlier. Okay, this quantity whose divergence is 0 can now be thought of as the curl of M. Okay, now once I do that, then you see. Then you see everything is consistent. Then if I take the divergence of this, then obviously this vanishes, and now my bound charge in the time dependent case not only has contribution from all these averaged effects of the spin and angular momentum of the atoms or constituents, but it also has contribution from the changing or the time dependent bound charges. Okay, so the bound charges are moving, that also gives rise to a current. Okay, so moving or oscillating rather, they are bound, so they cannot move around, but they can oscillate around and therefore by produce tiny currents. Okay, so therefore that effect is essentially contained in that effect is also contributing to the bound currents. But at the same time, you see there can be other effects like the spin or the angular momentum of the atoms, or roughly, some kind of quantum effects that is effectively captured in this classical sense or in this classical theory. That is, all of that effect is effectively captured in this definition of the magnetization. Okay, so this is what I have here. So if I have this, then I can write down Ampere's law in most generality, including Maxwell's correction. And then the current also I split up into two parts, bound and free. And the bound current I write as curl of M and del P del T. P is the polarization. But now you see it fits into the game very clearly, because this P goes and combines with the del E del T term, and this gives me my D vector. Okay, and this curl of M goes and combines with the magnetic field, and this gives me the H vector. So in terms of the H and the D, the same structure of the Maxwell's equation, the Maxwell modified Ampere's law, the same structure is valid in terms of H and D. It's just that, you see, the mu naughts and all these things have disappeared and they have been absorbed here. Okay, that's the only modification that has happened. Okay, further, we saw that the Gauss law, which was modified and written in terms of the D field in the macroscopic sense, which is given in this way. Okay, so these are the sources, therefore, the effect of the matter, in the sources, that has been taken into account in such a way that the equation with the source, the Maxwell's equation with the sources, they get modified, and the electric and magnetic field essentially get replaced by this D and H in general. Okay, so that's the only modification that happens. Okay, so you see the macroscopic Maxwell's equation therefore take this form, that two of these equations, or rather four of these equations, you write in terms of the D and the H, and the rest of the equations without sources, that you cannot manipulate, because there you cannot split up charge into bound charge, or there's no effect upon those equations. So those equations also, in an average sense, must be valid if you are trying to solve the system in a consistent way. Okay, so again, in this equation, it's some kind of an average macroscopic electric field and magnetic field also. Okay, of course these are average quantities, but so are these. That's what I want to advocate. Okay, so now these equations becomes too many equations. Okay, there is D, there is H, there is B, there is E. You cannot really solve them. In order to solve them, you need to know the E's and the B's in terms of the D and H. This is a very, very crucial point. You see, the way I have tried to develop it, these two equations are essentially some modification of the original averaged Maxwell's equation, where I have taken into account the effect of the bound charges and the effect of the bound currents and put it into these terms. Okay, but here there is no such scope. So here the electric field and magnetic field remains. So if I have to solve the combined system, I have to somehow know what this D and H are in terms of E and B. And as I said, in our simplistic model, or in simplistic for dielectrics, they are just proportional to each other with some proportionality constant. Okay, it's that simple. Okay, these proportionality constants are essentially differ from that of the vacuum. So all the effect of matter is contained within these two proportionality constants now. Okay, that's how interesting it is. And essentially, as I said, for most matter, this mu is essentially equal to mu naught. Okay, for most of the cases. Again, that may not be the case. Okay, there can be ferromagnetism, materials exhibiting ferromagnetism, etc., where this kind of thing breaks down. But again, we are not going to look into that at the moment. Okay, those kind of complications. Very good. Now, so that's it. You see, take this, plug it in here. Take this, plug it in here. Okay, here and here. Then you see we are back with the Maxwell's equation with just two constants differing here. Here epsilon naught becomes epsilon, and here mu naught becomes mu. That's it. Okay. So you see the effective description is also very similar to the description that we did. And then we solve those equations. You can play the same game. We can write down some effective potential and then try to find the retarded solution, etc., etc. Everything works out after that. Okay, at least in this simple case where mu naught and epsilon naught is a constant, everything works out. Okay, so then you can ask that, well, let's look at the simplest solutions, which was the electromagnetic waves. So let us try to understand if this admits, inside matter, if such electromagnetic waves are admitted, okay, or such solutions are admitted. Okay, and as you can see that, as I repeatedly emphasized, all the effects inside matter, inside matter, if there are no free charges, therefore I've set this thing to 0. I've assumed, let's say there are no free charges. So if there are no free charges, this is 0 and this is 0. Only thing that happens under this assumption is that this particular constant here, that changes. Okay, earlier it was mu naught epsilon naught, now it's mu times epsilon. Okay, for the free Maxwell's equation, without free charges, this is the case. Okay, and it's identical to the free Maxwell's equation in vacuum, just with this small modification here. Okay, but this is a very crucial modification. But think about the phenomenon that's happening. Let's say, so now as you can clearly imagine that this would admit electromagnetic waves, and it's true, we have light moving through water, light moving through glass, light moving through air, etc. Okay, that definitely happens. Okay, so whatever effective theory we write down, it better explain light moving through all these objects, right? So it does explain that, but at the same time, it does it with this little modification here, where mu naught epsilon naught is converted to mu n epsilon. Okay, and it's also easy to see the effect of this modification, because now if I write down the wave equation as we did for the electric and the magnetic field, again, what we essentially do is just take the curl of this equation and then basically replace the electric field using the curl of the electric field. Then I get an equation entirely in terms of the magnetic field, which is this one, and then I can do the same. I can take the curl of this equation. Okay, and basically I have to use them here when I use the curl, like when I do the curl. It's the same drill that we have learned. Okay, and this gives us these wave equations. But now the wave equations, this constant is different, right? This constant is different, and as you know, this constant determines the velocity of the wave. Okay, and because they are different, therefore these velocity of the wave inside matter is going to be significantly different from depending on the kind of matter. Depending how these coefficients are different from mu naught epsilon naught. It's going to be different. The speed of light in matter is going to be different than c, or the speed of light in vacuum. Okay. So that's the effect, and so now if I look for these kind of electromagnetic wave solutions, you will see that it is a solution. Again, the electric magnetic field and the direction of propagation, they form like the XYZ axis, this thing, and they are all mutually orthogonal to each other. And apart from that, there's this the frequency of this wave is related to this wave number by a velocity, and this velocity now is different from that what you will have in vacuum, and it's going to be a quantity v which is going to be less than c in general. Okay, so this will be something which is less than c, and this we have learned in relativity. Nothing can travel faster than the speed of light. Well, nothing. No signal. So therefore we have this condition which is in general seen to hold in all matter. Okay, so now so basically you see this ratio is basically called the refractive index of the medium. It kind of characterizes what this thing is. But as I said, mu naught is mu is roughly equal to mu naught. Then this n essentially captures what is the value, changed value of the epsilon compared to epsilon naught. It's just the ratio and the root over that. Okay, so that is what it is. Okay, so now there is a very interesting thing that happens, which is so as you can see, the velocity of light inside matter is less than that of c. Okay, so inside matter, there can be particles which is traveling greater than the speed of light in that matter. Okay, so this is some very interesting phenomenon that happens. Let's say you have let's say a charged particle which is moving at a velocity which is more than v. Okay, or the phase velocity, as I'll define later. Okay, let's say some charged particle is moving with a velocity u, which is and this magnitude of u is larger than the magnitude of v. Okay, then you will see that this thing essentially develops a kind of a cone. It's very similar to the effect that happens for sonic boom. Okay, that happens, and this moving charge particle, even if it is constant, let's say this u is constant. Okay, let's say this u is constant. Even if this u is constant, then in this scenario, it sends out radiation along this cone. Okay, it sends out electromagnetic radiation along this cone, and this phenomena, it has a name. It's called Cherenkov radiation. And again, Zangwill has a very nice description of this phenomena. Again, I'm not going to the details of it. I'll not have the time to do that. But you are highly encouraged to go and read, Cherenkov radiation from Zangwill. It's a very, very, very interesting phenomena. Of course, here you can see you don't need accelerating charges to produce this radiation. Okay, and you can ask that why that is the case. Because we know that I have emphasized so much that if it is not accelerating, then you don't have the radiation fields, and etc., etc. But you see here there is a very complicated phenomenon happening. As the charge is moving through, it's kind of making interacting with all the matter particles that is there, and it's making them dance around with its electric and magnetic field, and that can produce radiation. Okay, so effectively, microscopically, if you view it, that is what is giving rise to the radiation. Okay, there are things accelerating, there are charges accelerating. Okay, there are charge densities fluctuating. There are electric dipole moments that are fluctuating, etc., etc., which is giving rise to this phenomena. But you can also understand this phenomena, completely within the domain of this effective theory analytically. Okay, and that again has been described in a very, very nice way in Zangwill. So kindly look at it whenever you have the time. Okay, so very good. So this is, and this is again, this phenomenon is not possible in vacuum at all, because in vacuum nothing can travel faster than the speed of light. Okay, and therefore it's only because of the fact that the speed of light in matter has got reduced. Therefore, certain particles can actually travel faster than that light in matter. Okay, very good. So this is some very nice thing that happens. Now let me make life a little complicated, because it's kind of important, and just to demonstrate that, now we are like in this time, so far we have been talking about some very simple material where or that's also like we can see a lot of those materials around where epsilon is a constant. Okay, it's a constant, but it's like a response function, right? This is something which I want to emphasize. Okay, you see this alpha in terms of which this epsilon is defined. The alpha was the atomic polarizability. That is like a response to some average electric field that is there at that point. Okay, so because that is a response, therefore that response can actually have some kind of a frequency dependence. That depending on the kind of electric field that you are putting in, if it is oscillating with respect to time, then the response of the atom, how it creates the dancing dipole moment, that can also depend on the frequency. Okay, and if that depends on the frequency, then so will epsilon. Okay, so the epsilon can have for different frequency time, when there is a time dependent electric field, and then for different frequencies you can have different kind of responses, and that makes life very complicated. Epsilon is not a constant then, and we'll see that in such scenarios, in many materials that is the case, and in such scenarios, I mean in almost all material that is the case. It's just in that time omega dependence can be very very weak omega dependence, and then we can assume it to be a constant mostly. Okay, but in general there is a frequency dependence in general. Okay, and now we are going to try to understand what happens if this response is frequency dependent. Then what happens? That's what we are going to briefly discuss now. Okay, so if the response is frequency dependent, let us try to think about an electric field. Let's say some kind of you can think of it some kind of light, moving through matter. Okay, let's say there's some electric field which is moving through matter. Yeah, pardon my arrows. So right. So let's say I'm denoting the electric fields in this way. Okay, this you can this is also valid for an individual frequency. Okay, let's say for an individual frequency, the electric field had some had some frequency dependence, and then so if you just integrate this, then you will see that we are talking about the Fourier transform essentially in this side. Okay, so this is essentially the Fourier transform of whatever the electric field is. But let's not worry about the integral so much. Let's say that the electric field has this form where both this E, this macroscopic E, and the macroscopic D and H, they have frequency dependence. Of course, if the response is frequency dependent, then the effective electric field that forms there would also be frequency dependent, essentially. Okay, so this is a very good approximation for what happens inside matter for, let's say, light waves. Okay, which is oscillating, with some given frequency. Okay. So now in this scenario, as I was trying to say, the response can have a frequency dependence, and in that case, when we write down the equation relating E and D, that relation written in that can be written simply in Fourier space or in frequency space. Okay, where we are just thinking about doing the Fourier transform in the Fourier transform in time. Just if we do that, then this epsilon can have a frequency dependence. Okay, so if it does have a frequency dependence, then the corresponding time Fourier transforms of the E and D, they are related in this way. Sorry. Okay, and similarly, the time Fourier transform of the magnetic field and H, they are also related in this way. Again, for our purposes, what we are going to consider is that that is the strongest effect, that the epsilon is frequency dependent, and this mu naught is not so much dependent on frequency. In fact, as I said, for most materials, this mu is essentially equal to mu naught. So one can one can treat this as a constant in most of the cases. For complicated materials, this modeling just doesn't work. Okay, we have to rethink and remodel things like ferromagnets, etc. Okay, so essentially with this picture in mind, let us try to proceed and see what it tells us. That now, instead of saying that this guy is very simple constant, I'm saying that the epsilon or this response is dependent on frequency. So let us try to understand the effects. Okay, let's try to understand how the epsilon can depend on frequency. Let's try to understand that that possibility, how it can depend on frequency. Okay, So in order to do that, I will discuss very briefly a very, very simplistic model. This is a very, very simplistic classical model, but it's actually a very robust model because, it's a very gross modeling, but it works in, magically in a lot of cases, this kind of idea. Okay, so it's also a very good model for a lot of materials. But again, I must say that, all these things are, atoms are quantum and all these effects are quantum. So, this kind of modeling is a very an effective description, and then you have to go and check whether it works, and it works for many materials. If it breaks down, then you know why it's breaking down. There are some complicated effects that you are missing in this simple modeling, and therefore it's breaking down. Okay, so now with that in mind, let me try to understand what this epsilon or thing is where this omega dependence in epsilon may come from. Let us try to understand that. So for that, I'm doing a modeling of the atom. Okay, so for that, I'm trying to do a modeling of the atom. Again, let me draw the previous picture. Okay, so let's say I have this atom. Okay, so when I have this atom, this is the electron cloud that I have drawn. Okay, so in the electron cloud, so therefore this is some charge. Sorry, so this is some charge of the electron. Okay, this is some charge of the electron. It can be more than one electrons. So, this Q times some N times E, where, all these N's are the, total number of electrons in an atom, let's say, or in a molecule, or, whatever the microscopic, what are the macroscopic constituents that you're thinking about, those things. Okay. Therefore, this is some Q, therefore, I'm denoting it by some Q. And as you know, the electric field inside this, inside this electron cloud, that is given by this expression. Okay, the electric field at any point inside, okay, consider this to be the origin, firstly, okay, the center to be the origin. And if you consider the center to be the origin, let's say R is this coordinate, then the electric field is basically given by R by A cube. Okay, this you have done in your first assignment. Okay, this problem you have solved. That there's a charged sphere and, you had to find the electric field inside it. Okay, so in the first problem set, you have done that. Okay. So this is the nature of that. That is exactly what you're seeing here now, and this kind of electric field then would be proportional to this R, and it's directly proportional to this R. So it kind of grows, but then outside it starts reducing again. Okay, that's what happens. Okay, so therefore this is the kind of thing that happens, and so now let us say that, of course, what would happen is, now let's say you put in some kind of an electric field, then the cloud would kind of try to shift, but instead you can think that you are always at the origin of the cloud, and the plus charge which is there, that plus charge shifts somehow. Okay. So with that idea in mind, it's like equivalent, two equivalent pictures. Of course, the point of putting in an electric field is to create a plus minus charge separation, and therefore create this magnetic moment, electric dipole moment, and so basically that I am trying to describe in this way. Always thinking about the center of the electron cloud as the origin. That's the location of the negative charge. Okay. So if I do that, you see the force on the nucleus. That force is going to take this form because this is the electric field produced by the electron cloud everywhere inside. Okay. So if this is the force on the nucleus, then you can imagine that if there is no external electric field, then this force vanishes only at the origin, and therefore in that case the plus charge sits at the location of the minus charge. Okay, so that there is no force. Okay, so there is force balance. Again, it's a very simplistic way to think about it. But now if there is an electric field here, now in case there's a electric field here, okay, this is another scenario. Okay, now let's say there's an electric field. My circles are horrible. You have to pardon me for that. So if there's an electric field now, oops, sorry. If there's an electric field now, then if I again consider of course, the charge cloud moves in this direction, in the left direction. Okay, but I can think of that scenario as there's some force, that is, if the charge cloud moves in the negative, in the left direction, then basically the center of the charge cloud that I'm going to consider as my origin, and in that case, the plus charge will experience a force along the center of charge of the charge cloud, and basically, that is this force, and it's also going to experience another force along the electric field direction, which is this force. And if the forces have to be balanced in a static scenario, okay, this is the static scenario that I'm talking about, then we should have this E equal to this expression. Okay, the two forces have to balance. Okay, so if the two forces have to balance, therefore, then the location Rn, thinking of this as the origin, this minus charge as the origin, okay, then this distance is Rn, if you like, for the plus charge. Okay, so this gives us a good estimate of the distance, and it's kind of in a direction along the direction of the electric field. Okay, so if we have this in mind, then I can immediately define, so this is just some algebra, just bring it in this equation. You just take this R, and that is, find the equilibrium point, which I'm denoting by a subscript n, and this is the result for that manipulation. Okay, just bring it here. Okay, very good. So now with this Rn, I can define the dipole moment as Q times Rn, because that's my dipole moment of the configuration. Okay, and then this Q factor cancels, and I have this object is equal to E. So you see, in this way of thinking, this simple thing 4 pi epsilon naught a cube, where a cube is what is the a cube? You remember a cube was this effective size of the atom, that was A. In this formula when I wrote, this was the first time I introduced a cube, this A was the effective size of the atom. Okay, so if this is the effective size of the atom, then this is alpha would be essentially proportional to a cube in this simple model of, in the static scenario. Okay, and if this is proportional to a cube, from there you can easily figure out what epsilon is. Okay, epsilon is epsilon naught 1 plus chi e, epsilon naught 1 plus chi e is basically n times alpha by epsilon naught, and right, so now if you multiply epsilon naught, you get epsilon naught plus n alpha. N is the number density of the atoms again. Alpha is just in this model, simple model, is this quantity, and then you know what is epsilon in terms of epsilon naught in this way. Okay, so this is a very simplistic model of finding out what epsilon is, and in this static scenario, as you see in this model, okay, if the electric field is not time dependent, which I am assuming here, the electric field is not time dependent, then in this case, there is no frequency dependence here, because nothing is, there is no frequency to depend on. Okay, so this is just a constant. Okay, very good. So this is just a constant in that case. But now let's say I'm applying some kind of an electric field which is time dependent, and which I'm writing in this way. Okay, which I'm writing in this way, and if I write it in this way, again, sorry, I'm missing the vector signs. Okay, so if I write it in this way, then this electric field, when it encounters my previous atom, which was there, this atom that was there, right. What it is going to do is, it is going to create the charge separation, of course. It's going to create the charge separation, but this charge separation is going to oscillate to and fro because the electric field is oscillating here. Okay, so therefore, in this sense, it's going to give me an oscillating dipole like this. Okay, because the electric field is changing and the response is the dipole moment, which itself would be oscillating. Okay, but apart from just the electric field oscillation inducing a dipole oscillation, there is this effect that there can be a, so of course there can be a, this can also be a damped motion. Okay, so now again, now I'm like shifting the idea a little bit, like I'm thinking about the, let's say the charge cloud, which is kind of there's some plus charge here, and the charge cloud is dancing around this plus charge. Let's take the plus charge to be the origin now. Okay, in this description I said it was equivalent. All you needed to know is to find out what the dipole moment was. So if I do that, then it's the mass of this charge cloud, whatever it is, that acceleration would be given by this particular, of course, would be given by, of course, there's this force which is trying to, this force is trying to force the system. That means it is oscillating and it's kind of trying to force the system into getting into having a oscillation. Okay, think of this minus charge, and it's forcing the minus charge to move around this way. Okay, so this electric field, therefore, through its time dependence, is trying to force the minus charge to move around the plus charge. Okay, now apart from that, there is if the minus charge, if this electric field try to drag the electron cloud away from the plus charge, then there is a restoring force due to this object, due to the plus charge itself. Okay, and we have just calculated right now, what this restoring force was. Okay, because that is like the force experienced by this plus charge inside this thing, and that is also the force exerted by the plus charge on the cloud. Okay, so in that sense, this is like a restoring force which is acting, and it's the magnitude of the force is same, so I've kept it here. Okay, and it's also directed in the direction along which this electric field is trying to create the oscillation. Okay, in this the electric field is trying to drag it away, so that dragging will be like opposed. Whenever it is trying to drag away, there will be a restoring force which is going to oppose it, and this is that restoring force. Okay, apart from this fact, apart from these two forces, there can also be some kind of a damping in this oscillation that is induced onto this little atom. Okay, and this damping can come from a lot of ways. There are places where the atom can lose energy. One of the ways in which the atom can lose energy is by radiation damping. So when it oscillates, it kind of sends out radiation and it can damp. Therefore, okay. So that's one of the ways that you have learned. But there can be all sorts of nasty thing happening at the microscopic level, and the atom can lose energy in the that oscillation. Maybe in all that the physics of that oscillation has to be a damped oscillation. Okay, there is no other way, because the energy of that oscillation would be leaking out to all other degrees of freedom in the atom or at the microscopic level. Okay, and one of the ways in which it can actually also be emitted in terms of radiation, and then it will receive a radiation damping as well. This we have learned in our discussion of radiation. Okay, so there is some combined effective damping effect, which is essentially damping effects are proportional to the velocity. This is like a friction thing. Although we are talking about microscopic atoms, there can be friction in this sense, that there can be friction in the effective sense where energy is being lost to some other degrees of freedom. Okay, so this friction is proportional to the velocity. Again, this is a very simplistic model that I am trying to construct. So then now you see, this is basically the equation of a forced damped, it's like a forced, it's a damped harmonic oscillator. Okay, so it's a forced damped harmonic oscillator. Okay, but there's one point before it becomes a forced damped harmonic oscillator. You see, this location R goes and sits on top of the in the exponential here in the electric field when I write it down as a in terms of this Fourier transform E of omega. Okay, now if that happens, you see, then there is this R. Okay, this thing I was calling kz here above. So whenever I was talking about this was the kz, this part. Okay, this I can write as some k dot r. Okay, so this effect, the effect of this particular piece in the electric field, that would be negligible if my k, which is the wave, related to the wavelength, or it's the wave number, if the corresponding wavelength is large compared to the size of the atom A. Okay, if the wavelength is large compared to the size of the atom, the wavelength of radiation that is falling is large compared to the size of the atom, and in that case, the electric field over the atom, can be essentially the electric field of the radiation that is incident. I'm thinking about of this as some kind of a field due to some kind of a electromagnetic wave, let's say. Okay, that's what I have at the back of my mind. But this you can make more general, because you see some other time dependent electric field also can be written in this way. You just have to put in an integral here and do the analysis. Okay, but effectively that kind of thing. I'm just looking at individual frequencies like that in that kind of under that kind of a setup. And if I'm looking at individual frequencies, then essentially, because if you remember, I'm I'm looking to find the frequency dependence of epsilon. Therefore, it is okay to look at individual frequencies. And in that case, this is going to, if that wavelength of that fluctuation is large compared to the size of the atom, then effectively I can treat this whole thing as a constant. And if I treat this whole thing as a constant, this is just a forced harmonic oscillator, because this is just some sine function, forcing the harmonic oscillator. Okay. So this equation has, I can make this ansatz for this equation. Okay, this forced harmonic oscillator ansatz. This is just, physics 101. Okay, and so now you can just plug this into the equation. You get a omega squared here, minus omega squared. Okay, and this term remains as it is the forcing term. And then there are these, there are these terms that are there. In particular, there is this damping piece, which is here. Okay, so now you can solve for R naught, which is the amplitude of the damping. Which is the amplitude of the oscillation of this relative separation between plus and minus charge. Note that this is not the A. Okay, this is smaller than the A actually. Okay, it's a relative separation between the plus and minus charge, and that's the maximum amplitude of that. Okay, this R naught. So if I solve for this R naught, I find that this R naught is given in terms of this constant here. Okay, it's not a constant, depends on frequency, times this electric field here. And if I now take this solution and multiply it by e to the power I omega t on both sides, then I have R here. Okay. Then I have R here, and on this side I have the full complete electric field, which is here. Okay, and in this sense, now if I multiply with a charge Q on top of that, then I get the dipole moment, and this dipole moment essentially is given by this whole object here, the dipole moment of the atom, and this whole object is proportional to the electric field, and the proportionality constant here is called the atomic polarizability. Okay, but so therefore, you see, the atomic polarizability would have a frequency dependence. This has a frequency dependence here and here. Okay, and because it has alpha has a frequency dependence, therefore, we just derived, epsilon is expressed in terms of alpha. So epsilon, the permittivity would also have a frequency dependence if there is a frequency dependence in alpha. So that was probably obvious, because it's the same response function related to each other. I'm also considering it's a linear response. This kind of material are essentially linear dielectrics that I'm discussing. So this this kind of phenomenon, if you like, again there can be nonlinear effects, and there can be very very interesting stuff out there. It happens, and I'm just ignoring that discussion here. I'm trying to keep it simple. Okay, so but the most important noteworthy effect that I want to emphasize, apart from the frequency dependency, you see, whenever there is a frequency dependency, there is a natural imaginary part to the epsilon. And this imaginary part essentially comes from the damping, the imaginary part of the response. Okay, and you might ask that, are we talking about, these imaginary objects, then our physical things become imaginary? No, that's not the case. The electric field, etc., they're all real. It's not going to be imaginary. Okay, but in this description that we are trying to give, in this omega dependent description, our epsilon is going to become imaginary, and it must become imaginary. As I said, there are some physical effects which does produce this damping. This damping is a very real phenomenon. Okay, and therefore it does, this thing does acquire an imaginary part. Okay, and this definitely happens in almost all medium, where it's just that this effect can be very small, but this this imaginary part exists. Okay, so very good. I mean, the time scale associated with gamma can be very small. So in many cases, that's the only thing that comes into play. So but they exist very much. Okay, so very good. So now, if I take this, then now with this idea, the main thing that I wanted to drive across this thing is that whenever there is a omega dependence of the response, then the epsilon develops this imaginary part. Okay. Now, if it develops this imaginary part, then we see that this thing let's go back to this earlier description of the electromagnetic wave inside matter that we are talking about. So the electric fields are oscillating in this way. The D is oscillating in this way. They are proportional, but this epsilon has the omega dependence. Okay, that's what we wanted to capture. Now we can take this, take this and put it into our Maxwell's equations. Okay, then they give some respective constants. I'm using a combination. I'm taking this and putting it into Maxwell's equation, and I'm using this fact. Okay, here. Okay, then you see, it gives some interesting constants on the macroscopic electric and magnetic fields. Okay, these constants are very similar to what you have for electromagnetic waves. That k dot e is equal to 0. All these things. It's very similar, but it's just that the epsilon as a function of omega keeps hanging around at various places. Okay, and if it does hang around at various places, then you know that there exists a relationship between k and omega. If epsilon was a constant, then mu epsilon would have been the velocity. But now the epsilon has a omega dependence, and therefore this object, is a complicated function of omega. It's not a simple function of omega. Okay, it's a very complicated function of omega in general. Okay, so and we have seen, the kind of function of omega it is, from here. Okay, alpha is just, this thing, you plug it in here. Okay, so epsilon, the form of epsilon and alpha, it shares all the same features. So it's a, even in the simplistic model, the omega dependence is pretty complicated. Okay, and this omega, if you like, so this omega was this thing, this forcing term. This is something like a natural frequency of the system which is oscillating. Okay, that's why I'm calling it omega naught. Okay, and so omega naught can be written down in terms of these parameters, these atom parameters in the simple model in this way. Okay. All right, so with all of that in mind, let us proceed and see what we get. So this is some kind of electromagnetic radiation now. This is a solution with this fact that k square equal to this thing. And in this case, it is usual, although it seems that this is a complicated function of omega and k is simple, but it is usual to think of omega as a function of k rather than k as a function of omega. That is more usual. Okay. So, that is one thing that, we tend to, invert this relation and think of omega as a function of k. And whatever this functional form of epsilon is. Okay. And so at least in the various manipulation, this is what, we do, and this is what goes on. So basically now, if I take this, the main point now then becomes something very interesting. You see, that as I had argued that with the frequency dependence, the epsilons develops a real and imaginary part. This I am calling epsilon and epsilon 2. Then this relation would imply that the k also would develop a real and imaginary part. Okay, so the frequency is something real at the moment. Okay, at the moment I'm considering the frequency to be something real, but then because the response is the frequency is the frequency of the incoming radiation. It's just some real value. Okay. But because the response is complex, that makes the k complex in this particular media. Okay. If it makes the k complex, the complex, k1, k2 can be simply found from, by solving this equation here. Okay. By comparing real and imaginary parts of this equation, you can find what is k and k2. I'm just not writing down the relation explicitly. It's some complicated function. But it suffices, it can be determined. That's the point. Looking at this expression for alpha that we know, we can explicitly determine epsilon 1, epsilon 2, and then with the epsilon 2, we can explicitly determine k1 and k2. The real and imaginary parts in this model can be determined entirely in terms of the atomic parameters and all these things here. Okay, in terms of omega naught and omega and m and q, all these things. Okay, so very good. So if I do that, then now let us see what the expression of the electric and magnetic field looks like. So if I see what the expression for the electric and magnetic field looks like, again going back here, this was my form. Now k has an imaginary part, but because k has an imaginary part, therefore it comes out as this e to the power minus k2z. Okay, if it has an imaginary part. Okay, and as you can see from here, because of this imaginary part, this thing is like it's like damping the amplitude. Okay, the amplitude is going down as we move along the distance. Okay, so so this is something which is very curious. Okay, so so that's one that's one very important point. And so now we can do it for the magnetic field. We know what is the relation of the magnetic field and the electric field from what we have here. So again, my k direction is the z direction that I have used, okay, because I'm using kz. So my k direction is the z direction. So if you just use that, then you can figure out what the magnetic field is from the electric field. It's just given by this. But here, you know, what sits here is the k, which is a complex number now. Because it's a complex number, then I can write it as the magnitude of k e to the power I phi, because, you know, phi is some phase of the complex number. Okay. So now, in this particular scenario where you have this frequency dependence, you see, then there is an additional phase in the magnetic field compared to the electric field. So if I write it in terms of, you know, this expression, in terms of real and imaginary parts, I will see that there's this effect, which is, you know, which is basically making the amplitude go down with distance. Okay. And if you remember, you know, this imaginary part came down from some kind of a damping, right? So therefore, you know, this, you can imagine that it kind of like reduces the amplitude in some way. Okay. This is what is going on here for this e to the power minus kz. You know, this is a difference between electromagnetic waves inside the, you know, inside a dielectric, where the response has a frequency dependence, okay, and also has the imaginary part, okay. That is the consequence of this, because k2 was the imaginary part, you know, that is what, you know, I had drawn out from here. K2 was the imaginary part, right? So that is what I have drawn out from here, okay. K1 was the real part of k, K2 was the imaginary part of k, okay. So if I yeah, so basically this is my e to the power minus k2z, which is there. And the most important point, you know, so I have repeatedly emphasized while talking about electromagnetic waves in vacuum, that the magnetic field and the electric field were in phase. It had to be, because it had to solve Maxwell's equation. But now we see, if this has to solve the macroscopic Maxwell's equation, the B can develop an additional phase, because K is complex. And this phase again comes from the, if you like, you know, the effects of the damping term. Okay, that's why the phase comes, and that goes and sits into the magnetic field. So the magnetic field is off from the electric field with a phase phi, which is the phase of the K. Okay, so this is very, very interesting phenomena, that the magnetic field is off from the electric field with the phase phi. So this is what happens for electromagnetic waves inside matter. Okay, not in vacuum. In vacuum it has to be in the same phase, but inside matter, the magnetic, you know, that phase is also fixed by the properties of the matter, but it can be different in different matter. Okay, like, you know, it can have different values in different kinds of matter. Okay, it's essentially you know, very much defined by what kind of material the electromagnetic wave is going through. So these are the two new features of the electromagnetic phase of waves that has emerged within a material with a frequency dependent response and an imaginary part to the epsilon. Okay, that's the conclusion. Very good. Now, so now you can ask that, you know, what is the velocity of this wave? Because k is complex, so you don't know what to do. So you know, there are two ways to define the velocity of the wave. You know, because you know, one way, if you just have one frequency, okay, then you can just you know, take one, omega by k, you know, k1, where, you know, this is the k1, this is the propagating part. So from here you can say that you can define a velocity, which is you know, this velocity, you know, of the this thing, velocity of the velocity in which, you know, this phase travels. Okay, that is the velocity in which the phase travels, and so this is called the phase velocity. Okay, this is just omega by k. Okay, and so there's something else that you also define. I'm just giving you a very, very heuristic statement here. I mean, again, this will be like very, you know, you would know that this is very, very, this can be done better, much better, you know, than this discussion. I'm just trying to give you a very quick discussion. I mean, just in case you haven't seen this, I mean, these kind of ideas will be developed later in your courses on optics, etc. Okay, or even you know, to some extent in various courses in condensed matter, etc. But now this Vg is the group velocity. So when you talk about group velocity, that means you are talking about a scenario where you know, this particularly becomes very useful when you have a bunch of waves together with different frequencies. Okay, when you have a bunch of waves with different frequencies, then this group velocity is very useful in giving the description. Okay, why is that so? Let me just, you know, give you a very brief way to understand it. I mean, like, again, this can be done much better, I think, but just to give you a complete description. What happens is, so of course, as you can see, there are two things. There's omega by k, k1. K1 is the real part. Okay, so there's omega by k1, that is the real part. Real part of k. So you take omega, which is real, divided by k, that defines the velocity, that's the phase velocity. Now the group velocity, as you know, as I was trying to say here, you think of omega as a function of k, and then you find d omega dk. Okay, you find d omega dk, that gives you, so this is something different from this in general, if epsilon has a omega dependence. Okay, because then, omega can be a complicated function of k, so omega by k may not be omega, d omega dk, because if this is some, this dependence is not linear, then this is not just some, this is not equal, phase velocity is not equal to group velocity. Okay, but why define this d omega dk1? Okay, looking at this expression for a single frequency, it doesn't look so useful, but if you have an integral like this, where you have, many superposition of several frequencies, okay, and then there is a peak frequency. Okay, there's a peak k, in terms of k, because omega you are thinking as a function of k. Let's say there's a peak k at k naught. Okay, there's a peak. Okay, it's like a peaked at some value of k, which is k naught. Okay, so I mean this e is peaked at that value. Okay, so if this is the thing, then this is somewhat this is somewhat like the in the k along the k axis, this function has like a peak, like this. Okay, so in that case, you can take this argument, whatever appears here. Okay, you can take this argument and you can try to write it out. Okay, you can try to write it out in a Fourier series expansion about k naught. Okay, so sorry, you can try to write it out in a Taylor series expansion about k naught. Okay, if you write it out in a Taylor series expansion about k naught, then you will see that there's this term, this is the first term, and then there are dots, which I'm not caring at the moment. Let's say I'm very close to k naught. Let's say it's very peaked, very much peaked. I only care about k's, near k naught. Okay, in that case, under that approximation, I can ignore all these higher order things. But with that, you see what is happening. Now I can bunch together some of these terms. This thing is my group velocity that I'm referring to as group velocity. This can be bunched together. This term can be this k naught term and this term can be bunched together, and this is some some kind of a frequency, omega t kind of a thing that comes in here. But this other term where I take this kz and I take the k from here, take k common, then I see that this goes as z minus vgt. Okay, this tells us that this thing tells us that under this approximation, the p is moving at a velocity which is vg, essentially, right? So therefore, you see, that's why it's called the group velocity. It's like the peak of the group is like moving at some velocity vg. Okay, that is what is happening here. Again, I will stop the discussion here for such dispersive media, etc. discussion. Okay, that you are, I don't have, it's a huge thing. Like, you can go on discussing about it. But I mean, huge meaning like, it's like this thing. But again, we don't have time to discuss all that here. So I'm going to skip all that at the moment. Yeah, but this was just to give you a brief idea about what is going on and how to think about the frequency dependence. Okay, so when there's a frequency dependence of epsilon, there are all these interesting effects that are happening. Okay, and there can be a lot of very interesting effects that happens in this particular wave. Okay, so some of which you have done before and seen before, and some of which you are going to see again. But I'm just trying to give you an idea where how things fit into the big picture. That's what I'm trying to do. Okay, very good. So now, hopefully this will be useful. Like anyway. So this now, here this is the main reason why I'm getting into this discussion, because there's a very interesting thing happening here. Okay, and the very interesting thing that happens here is as soon as omega becomes frequency dependence and it develops an imaginary piece, there's some non-locality that comes into the game. The relationship between t and e becomes non-local in time. Okay, so this non-locality in time is an intrinsic feature of this omega dependent frequency. sorry, frequency dependent epsilon, sorry. Okay, this is a feature, which you cannot avoid, as I will try to argue now. Again, I find the discussion of this phenomena excellent. It's given in Jackson. So what I'm going to tell you now is essentially taken up from Jackson. This is the page number, and this is a very, very nice discussion of this phenomenon that happens. And actually, I have never seen a better. Everywhere they try to discuss this, but they mess it up very badly. But Jackson has a beautiful discussion here, which I'm trying to follow here. Okay. So what is, how do I see this non-locality coming up? Okay, this non-locality comes up essentially because of the following thing. You see, as I said, these are some time Fourier transforms. This part you can, you can say that you haven't done any Fourier transform. The X part, you have just done the time Fourier transform. And even then, whatever I just said, just follows through. So now, if this right now, if I have this kind of a relation, then if I have this kind of a relation, then right. If I have this kind of a relation, then I can do the Fourier transform of D. It's given this way. I can do the Fourier transform of E. It's given this way, and this is the inverse Fourier transform. Okay, here E of omega is related to E of t in this way. Okay, now you see, as soon as I say that this relationship I can take and I can plug it back in here. So this will give me the way in which dx of t is related to the E as a function of t, because I am doing the omega integral. Okay, so this is exactly what I am going to do. Here d of omega, I'm going to take this and put it into d of omega. That's exactly what, take this and put it into d of omega. So if I do that, I have this thing here. Okay, now if I have this thing here, this omega times epsilon here, where this, this epsilon times E here, where this epsilon is omega dependent. Okay, so then you see, then I can do a few algebraic manipulations. Okay, what are the algebraic manipulations I can do? I can do the following algebraic manipulation, that I can say that let me, this omega integral, that I can keep outside. Okay, and I can take this E of x of omega and then use this inverse Fourier transform. Okay, and plug it back in here. So now there is a time integral that enters the game. Okay, this t integral that enters the game here. But again, because there is a t already, I'm sorry. Yeah, but because there is a t already here, yeah, sorry. So essentially what I did, take this and plug it in here. Okay, and then the E of omega, I just use the Fourier transform and plug it in here. Then I have one integral over d omega and the other integral over this thing. Now here, when I plug this in, this is the integrated variable, so I put a prime here and then plug it in. Okay, so there's a prime here, prime here, prime here. That's what this is. This is exactly equal to this, this value here. It's the Fourier transform. Okay, so once I do that, I see that I can take now my epsilon and write it in terms of the the electric susceptibility as epsilon naught times 1 plus. This epsilon naught I can pull outside, and then this term becomes, there's a 1 plus chi e, this kind of a term. Now the term which is 1, you see, there I can very easily, the d omega integral, this I have taken and clubbed it here as written as this term. Okay, and whereas this chi e, for the chi e, also I have taken the d omega integral. Chi e is also a function of omega, is epsilon is a function of omega, right? So this chi e integral, d omega integral over chi e, that I have written here. And as you can imagine, as you know very well, this is precisely equal to the delta function, which is going to set this t prime to t. Okay, this is a delta function. Okay, so maybe it's worthwhile to write. This is a delta of t minus t prime. Okay, and this function is nothing but the Fourier this object is nothing but the Fourier transform of this is what it is. So the g I have written here. Okay, so this g is nothing but the this whole integral is the Fourier transform of chi e, susceptibility. Okay, so this g is the Fourier transform of chi e. Okay, so if I write it as a Fourier transform of chi e, then I can write it as g. Okay, then there is epsilon naught e. Okay, which is already there. So d of x of t, I can write as epsilon naught e of x of t. Okay, this t is the same t as here. But then there is this additional term, because chi is omega dependent, because of that fact, there is an additional term here, which is this e of integral over e. Okay, and so what I have done here is very simple. That this one is the Fourier transform. So Fourier transform, it's a t minus a t prime. That goes in here in the argument, and then I have substituted this integral variable t prime. I have called that t prime t minus tau. So if it is t minus tau, as far as t is concerned, it's constant, so it doesn't matter. Right. So therefore, I could write. So right. So I can write this in this way. Yeah, this is just a mere variable substitution, if you like. Okay, converting the t prime integral into the tau integral through this variable substitution. Okay, so right. So now, right. So this is the expression which I want you to focus on, and right, and this is the expression. Right. So yeah, sorry, there's a little bit of a thing, while describing this Fourier transform. So let's see. So here, right. Let me see. So. Yeah, so this is correct. Right. This is also right. So, okay. Right. Okay. Okay, so essentially, this is the expression that we have, and so in this expression, we want to check whether what is going on. Okay, so as I was trying to point out, that this t is equal to this t out here. Okay, this t is equal to this t out here, but you see, this t here, it comes from the t here. Okay, so this is the relationship between d, e, and t. Okay, so this t comes from this t out here. Okay, and so Yeah. Yeah, 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 right. So essentially, uh, yeah, right. So basically, I have yeah. So just going ahead, this this d. Therefore, you see what is going on. This is t minus tau, and there's an integral over tau. So in order to know the time, know the d at, in order to know the d at a particular value of time, I have to know the e at all values of time, because you see there's an integral here. So I have to know the value of e at all values of, so the average e I need to know at all values of time in order to know what is my d at a particular point in time. So that this is the idea why it is, this one is a this why this one is a there's a non-locality in this sense, that this expression, the relation between d and e is not local in time, but because of this integral it's non-local in time. And as long as this g of tau is non-zero, okay, this g of tau essentially is this g of tau essentially is the Fourier transform of the omega dependence of chi. Of course, if there is no no omega dependence, then this object would also give a delta function. Okay, and if this gives a delta function, then we can see that. So let's say this is some constant chi e. So if this is some constant chi e, then this will be some. So this epsilon naught multiplies everything. It just pulled out. So this epsilon naught multiplies everything. Okay, both the terms. Now if there's a chi e here, which you can pull outside the integral, then there's a delta function which gives you a e, and here you will have a epsilon naught 1 plus chi e. Okay, that you will have. So that is again going to give me a so the delta function here, this delta function here is going to essentially set t equal to t prime equal to t, and this is going to give me my epsilon. Okay, d will become equal to epsilon e, and then everything will be local. Okay, but because that there's this frequency dependence, therefore things are non-local here. Okay, so this is a bit of a this is a fact. You cannot do anything about it. It is non-local. Okay, it's not a problem, but this effective theory and the relation between d and e, which is essential to solve this theory. If you remember, I have to give you a relation between h and h and b, and I have to give you a relationship between d and e. Okay, so if I have to give you a relationship between these two quantities, then I must tell you what this. I must tell you what this. I must tell you what this relationship is, and if the if the epsilon is frequency dependent, then this relationship is non-local in time. It's non-local only in time, but it's for space, it's local in space. Okay, so it's non-local only in time. Okay, okay, just moving on. So basically now what you can do is, from the expression of the alpha that we derived in our particular model, okay, you can try to find out what is chi and find its Fourier transform. You can just find what is chi from alpha, okay, and once you find chi, you can try to take the Fourier transform of that to find this function g. And as you can see here, because of these interesting pole structure, it's a very interesting integral, and you can do a complex contour integral to find the omega. So omega you can analytically you can take this and continue into the whole analytically continue into the complex plane of omega, and then you can try to do this integral considering the considering a suitable curve in the complex plane. And if you do that, then you will see that from that kind of contour integral argument, which probably by now you have learned contour integrals. By that contour integral argument, you will see that there is a theta of tau that comes in the function g of tau. Okay, it's only because there are some you have to be careful about what what this tau is in the Fourier in taking this performing this integral. You have to this is tau here. Okay, in performing this integral, you have to be slightly careful. When I say that this is tau here, so you have to be particularly careful because you have to be particularly careful because you have to be careful how you close the contours. Okay, you have to be careful how you close the contours. From there, essentially you get this theta of tau. Okay, and because you have done contour integrals in math method, so and this is a particular model again. So I will leave this exercise to you to actually work out this g of tau. Okay, I mean this one is also just mentioned in Jackson. It's not worked out. So you will have to do some work if you want to work it out. Okay, so you can try to work this out, and if you do, then you will see that this step function theta is present in g of tau. This is a very, very crucial and important step function. This theta, its presence is very important. Okay, as I will try to explain now. Okay, so what happens because of this step function? If you just take this and combine this with this gamma is the damping factor gamma. Okay, that we had in our model. Okay, and this nu naught is basically this expression. This is the natural frequency. Okay, so if you have this damping factor, then if I plot these two functions together as a function of tau, okay, then you see it has this form. Because of the theta, it is 0 all throughout negative tau, and for positive tau, it kind of rapidly decreases because of the exponential. Okay, and this roughly the extent to which it is non-zero in tau is this object is given by gamma inverse. So this function g has support only for a finite amount of tau, only for a finite tau, and that finite tau for which it is non-zero essentially is given by gamma inverse. Okay, and so therefore you see this function here is non-zero only for a duration in tau, starting from 0 to gamma inverse, roughly speaking. Okay, because this integral, because this function is 0 outside that effectively. Okay, so therefore because this function is 0 outside that, therefore the non-locality which comes from this integral is only limited to the extent of gamma inverse, and if this number is very small, if this time is very small, then the non-locality is contained within a small time. Okay, so that's what happens. Okay, so this is this is the picture for the particular model. Okay, but this statement here, as you can see, here I have not made any assumptions about the model whatsoever. Okay, this it was just followed from the fact that epsilon had a frequency dependence. Okay, this just followed from the fact that epsilon had a frequency dependence, and if this epsilon has a frequency dependence, then the extent of but in a particular model we saw that the extent of non-locality was contained with the value of tau which is greater than 0. Okay, now if the value of tau is greater than 0, then you see, then this term here, t minus tau, if the value of tau is greater than 0 always, okay, then this t minus tau, this thing is less than t. Okay, so you see, it's as far as this non-locality is concerned, it doesn't care about time which is ahead of the time here at which we are measuring d. Okay, this time for which I need to know the electric field is at a time which is earlier, because of this nature of g, why it is by which it is 0 for tau less than 0. Okay, because g of tau is 0 for tau less than 0, therefore I need not know the electric field at an advanced time. Only if I know the electric field at earlier times, that suffices for me to know what the d is. So although there is a non-locality, but the non-locality, because of the presence of the theta, is not acausal, in the sense everything that happens before predicts what is my effective d here. Okay, that is the point. Okay, so this theta function here in this particular model that we are doing, we are looking at in this particular model, this theta, essentially restores causality because of this fact that, because of the theta, this integral effectively starts from 0. Because it effectively starts from 0, because of the theta here, because it effectively starts from 0, therefore, this, I need to know the electric field only at earlier times compared to t. Okay, and therefore, that is a statement of causality. And as you know, that causality is an important principle that we don't want to give up. Because causality is an important principle, then it better be that this fact that g depends on theta of tau is a model independent thing. Here, for a particular model, I derived that there was a theta, theta of tau. It's proportional to theta of tau. But this g of tau in general must be proportional to theta of tau. Otherwise, there will be a violation of causality. Okay, because that violation cannot happen. Therefore, g of tau must be proportional to theta of tau. This is the physical input of causality that you can say independent of the model. Completely independent of the model. You should be able to write down. You should be able to write down this statement that g must be proportional to theta of t. Okay. Otherwise, causality would be violated. I hope this point is clear. This is very, very important. Okay. And then not only that, d and e, all these quantities, they must be real. So g of tau must be also real. Okay. These are two important things, that g of tau, although I saw that epsilon and chi e, all these are complex quantities in our model we saw. But g of tau, after you do the Fourier transform, that must be real. And that we are seeing also in this particular model, although there were, complex dependencies, but when I did the Fourier transform at the end and found g of tau, it is a real quantity, completely real quantity. There can be some number here, which I didn't write down. Okay, but you should do this integral and find this number. This number is proportional to this thing, this thing in chi e. So you convert this to chi e, and whatever is in the numerator is proportional to here, this number. Okay, very good. So that is what is going on. And so now if I define epsilon omega by epsilon naught to be 1 plus chi e, this is a function of omega, this is a function of omega, both are complex, and then the Fourier transform, this object is given by the Fourier transform g of tau in this way. So now from here on, I'm saying that I will make a model independent statement. Even for any model, okay, this is a model independent statement. Okay, so this is a model independent. Okay, this is a model independent statement. So this thing is very important. Now we are taking a point of view that although we figured out what g of tau is in a particular model, okay, although we figured out what g of tau is in a particular model, but this object, this statement was model independent, and now we are going to say that these two features of g of tau, because of the physical condition that these fields, electric fields must be real and d must be real, and there should be causality, these two properties of g of tau must be true. Okay, for any model. Okay, what do you consider? Now, with this two in mind, then this g has these two properties. Okay, this g of tau has these two properties. Okay, and if g of tau has the property that is proportional to theta, then this lower integral, I can say that while doing the Fourier transform, I can do an integral from 0 to infinity. Okay, instead of doing from minus infinity to plus infinity, I can do from 0 to infinity. Okay, so if I do from 0 to infinity, then there are two things. Firstly, if g has to be real, then as you can see, I can say that omega goes to minus omega. If I go to minus omega, then I'll get a minus sign here. If omega goes to minus omega, then I get a minus sign here. Okay, sorry, here I shouldn't write the minus sign, otherwise it will look. So if omega goes to minus omega, then I will get a minus sign here. Okay, and if I get a minus sign here, then I will try to right. If I get a minus sign here, then essentially I can rewrite this as saying that I take a star on this and a star on this. Okay, so if I take a star on this, then you see, then I get a minus sign and a star here, and the star of a star is omega again. So therefore, this statement must be true. Okay, so it's just a fact that epsilon omega has this form where g of tau is real. Okay, from that fact that this is real, this equation follows. Okay, and not only this, the main point is this fact that it starts from 0 implies that our epsilon should be an analytic function in the upper half plane. You know, there cannot be any singularity in the whole upper half plane. Okay. Upper half plane meaning, you know, now I am trying to think of, you know, when I am making this statement here, you know, it is very important. You know, when I am making this statement, I am assuming that my omega is a complex omega. Okay, for both these statements. Okay, at this point, now, you know, up till now, whatever we discussed, we are thinking that omega is real. But now, in order to analyze, you know, what this object is, I will continue omega into the complex plane and I will think of omega as a complex number. Okay. So, so that's what I'm going to do and study it in the complex plane. Once I do that, then, so again, this is very important. Up till now, it was real, but now I'm thinking of this as a complex. And if I think of this as a complex, this is a property which follows from reality. And the other property of epsilon omega that follows is the fact that it is an analytic, you know, complex analytic function. When I say analytic function, I mean it's a complex analytic function in the upper half plane. So in the omega plane, so only when imaginary omega is greater than 0, in this region, it is a very well-defined function which doesn't blow up and, you know, completely, you know, derivatives are well-defined everywhere. You know, that is what it is. Okay. And as you can see, why it's only in the upper half plane? Because you see, this I can write as omega 1 plus I omega 2, right? And if I write it in this way, then the I omega 2 is going to give me a e to the power minus omega 2 tau. Okay. So if omega 2 is positive, which is the upper half plane, imaginary part of omega is positive, then this is a completely, perfectly well-defined integral. But if this is negative, omega 2 is negative, that means in the lower half plane, then there can be singularities arising from the fact that, you know, this tau integral goes up to infinity. Okay. So that, you know, it has a bad behavior there. Okay. So therefore, from the expression here that I have written, I can only say that it is an analytic function in the upper half plane where it's perfectly well defined, provided G is finite. You know, this is another important point. Okay, provided G of tau is finite. Okay, if G of tau is finite, then it is an analytic function in the upper half plane. Okay, again, for dielectrics, this is always the case that G of tau is finite. But for conductors, etc., you know, you might have to deal with a pole at epsilon at omega equal to 0. But again, I'm not going into that discussion here. Okay, so so here for dielectrics, this is always the case, and you know, this function is well defined in the upper half plane everywhere. Okay, yeah. Right. Also, you know, I should mention that you know that it is not analytic in the lower half plane. In fact, there are poles because, you know, this alpha. If you look at this alpha, if you look at this alpha, there are poles in the imaginary, you know, in the negative imaginary thing. Okay. So right. So if you take this alpha and find the corresponding if you take the alpha and find the corresponding epsilon, you will find that there are poles in the imaginary in the negative imaginary thing. But in the model, again in the specific model. But again, here I am trying to do a model independent discussion. So all I need for this to be true, that as a complex function, it you know, epsilon to be analytic function in the upper half plane, all I need here is that this integral starts from 0 and g of tau is proportional to theta of tau and is finite everywhere. Okay, that's all I need, which is there in the model that I discussed, but this should be generally true, otherwise causality would be violated. Okay, so that is a very important point. That physical requirement of causality essentially enforces this fact. Okay, this is a very important and interesting fact, that's why I hope it is clear. But now if it is an analytic function, then this analytic functions can be written in this way. Okay, this is the analytic function, this minus 1. Okay, this minus 1, that is chi essentially. Okay, so this epsilon naught, sorry, epsilon naught. Okay, so this minus 1, this, think of, although I have written epsilon naught, following Jackson, I have written this combination. Think of this as some f of z, and think of think of this whole combination, this one and this whole combination, think of this as some f of z, and then this is some that same f of omega prime, and then divided by omega prime minus z d omega prime, and z is any point in the upper half plane. Okay, it's any point in the upper half plane, and this contour integral c is essentially this contour, which is this radius is basically this radius is infinity. Okay, so it's a big the full half circle, the full upper half plane, over which you do this contour integral. Again, this, you just start from a little below the real line. You also include the real line, and basically you complete this contour containing the full upper half plane. And then if you do that, then all points in the upper half plane, because it is an analytic function, it can be written in this way: that there is a single pole here. Okay, and by Cauchy's theorem, this is just an identity. Then, okay. So essentially, we see that we can write this function in this way, and once we write it in this way, then what we can do is we can do the following. That again, from the fact that it is this thing is an analytic function, and from this fact that, as I told you, if the omega 2 in the upper half plane, this has a form e to the power minus omega 2 tau, this thing, this has that form. Therefore, this object here essentially goes to 0 at omega omega 2 large. Okay, so on this circle, on this circle, the contribution from this sorry, it goes to 0 for all this thing. Okay, on the so what I mean is the contribution from this circle, from this big circle, that vanishes because of this structure, because of this kind of causal structure for this epsilon omega by epsilon naught. Okay, and if the contribution vanishes, then this contour integral therefore just have contribution from the real line. Okay, therefore I have minus infinity to plus infinity omega prime. So now we are back to real line, except that this point is any point on the upper half plane. Okay, this point z is any point on the upper half plane, so that z is any point on the upper half plane, but this integral is over the real line, because the contribution from here vanishes. Okay, so this is such a function that the this function goes to 0 sufficiently rapidly at at distances far away. Okay, here also this is one thing that I'm assuming, like here if I right, so I mean this thing I have mentioned that G is finite everywhere. But it's not only finite. I mean, I also want G to go to 0 rapidly at t, for large tau. Okay, I want that also to be true. Okay, so so very good. So now I just take this fact that there's a point here, and this point is any point on the upper half plane. So I can, but now this integral has become a real integral, and I'm also interested in real values of this argument here, right? So I want to take any point z in this formula and take the z point and bring it close to the real axis. So I want to take points here and any z here and bring it close to the real axis. Okay, this I do by assuming that z is to any point in the upper half plane. So z is some omega, this is the real value of omega plus I delta delta, this is a small delta, and I'll take the limit delta tends to 0. Okay, I'm interested in the limit delta tends to 0 as I approach with the z on the real axis. Because ultimately I'm interested in epsilon omega where omega is real. So this one, I want to make this real, and therefore, but I know this at points in the upper half plane. But therefore, I want to take this point on the upper half plane and approach it to the real line. And that I can do by just substituting z equal to omega plus I delta. And if I do it here, z, I just substitute it here in this way. So if I substitute it here in this way, then I see that there is a denominator which has this nice form, that this denominator I can write the principal part of 1 over omega prime minus omega plus this delta function. This is the contribution from the little tiny semicircle. Okay, this delta function is there. Okay, I'm sure you might have seen this in your math method, while you are doing the contour integrals. So this is the principal part of 1 by omega prime minus omega. And so now if I plug this back into our formula, I will see that, there will be this principal part term, and then there will be a term because of the delta function. The delta function will click and make this omega prime omega. Okay, in this, when I put it into this integral, and when it becomes omega, then you see there's a factor of half coming. So this half will cancel the half here. This will give me a half of this, and this minus 1 will cancel the, minus 1, become minus half, and that will cancel my, that will reduce my 1 to half, and the factors of 2 will cancel in the denominator, and I'll be left over with this expression here. Okay, this is the expression that takes into fact, that ensures, not only ensures that the omega, the epsilon, this function is analytic in the upper half plane as a complex, this thing, that thing has gone into it, and therefore causality has gone into it. So this relationship, takes into account causality and the fact that the electric and magnetic fields, the electric field and the D is a real quantity. Okay, although epsilon is complex, but we have ensured that although epsilon is complex, but because of this relation, I'm assuming G is real. Therefore, E, and D, all these things are real. Okay, all these things are real, and therefore, I think our right, and therefore, these things are all physical. So everything that has come out of it is physical. So although epsilon is a complex quantity, everything that comes out of this complex quantity, all physical things that come out of it are all physical, are all real quantities. Okay, and not only that, causality tells us, causality implies that this function, this complex function, should satisfy a relationship like this because of causality. Okay, we have used the causality input for the analyticity in the upper half plane, and from there we deduced that the form of this function is this. So now we can just take this function and find the real and imaginary parts. So if you like the real part of this, there's an I here. Okay, so this will give me the imaginary part of this. So the one right. So right. So if I write down the imaginary part of this, so think of this as epsilon 1 plus I epsilon 2. So the real part here, I have a epsilon 1 plus I epsilon 2. Okay, I epsilon 2. So this epsilon 2 will be captured here. So the imaginary part, this one will be captured here. This one is this I is going to just cancel this I here. Okay. So the imaginary part, if I take the real part on both the equations, then the imaginary part is going to contribute here and come here, and the real part on the left hand side. So the real part in this way gets related to the imaginary part if I just take the real part of this equation. Okay, because of this I here. Okay, so that's nice. That's something nice. How about if I take the imaginary part of this equation? If I take the imaginary part of this equation, then there's the real part epsilon 1 which remains here, the real part, and the 1 also remains here. This one. So when I take the real part, the 1 remains, but when I take the imaginary part, this one doesn't contribute. Only epsilon 2 contributes here. So that's the imaginary part which remains. And here, from here, both the term would remain, because the real part, the full real part of this and the 1, that would both remain here. Okay, so it's just these two expressions just follow from taking real and imaginary parts of this complex expression. Okay, and if I take the real and imaginary parts of this complex expression, then this is the relation that I get, and right. So and this minus sign is essentially because when I take the imaginary part, this becomes 1 over I times epsilon 1, sorry, 1 over I times epsilon 1, that is minus I epsilon 1. This minus sign is basically this minus sign. Okay, very good. So this is essentially tells us that the real and imaginary parts of the epsilon, when they have the real, when it is a complex number, they must be related to each other. And where does this follow from? This follows from causality, as we just saw. Okay, it just follows from the fact that the D and the E relationship must be causal, although it's non-local, but it must be causal. Okay, although it's non-local, it must be causal, and because of that fact, the response cannot, must have a form that its real and imaginary parts are related in this way. Okay, that's, when this is true for epsilon, it's true for chi, in fact, the chi combination is already present here. So it's true for chi, it's true for all these objects, okay, alpha and everything, okay. And there's something more that you can do. You see, you had this fact which followed from the fact that g of tau was real. So now, and now you are doing an integral over the real, over the real line. Okay, so every omega here, now you can start thinking as the real thing, because here also z you have taken to the real axis, so this is all real now. Okay, although this discussion was done with complex omega, but now again I'm reverting back to real omega. But if omega is real, then the real part of this is equal to, minus of omega is equal to the real part of this. Omega is real. So, I'm just comparing real and imaginary parts of both the solutions, both the sides. Then the real part here must be equal to the real part here. And the imaginary part here, because there is a star, should be equal to the minus of imaginary part of here. So the real part is basically an even function and the imaginary part is an odd function. It just follows from here when omega is real. Okay. It just follows from the fact that g of tau was a real thing. Okay, that from there it followed. Okay, in general, in a model independent way. So again, this is also very much model independent. Okay, here the only input is causality, and you can of course go into this model that we did and calculate and see that it is model independent. Very good. Now you can just use these facts here a little bit. So, in order to, you can take this minus infinity to plus infinity integral and convert it into 0 to infinity integral by using that this is an even function, and then, so here in the numerator imaginary part appeared. So, this is the odd function that you have to take. There is a minus sign because of this odd function. For the thing from minus infinity to 0, there is a minus sign. Therefore, it is plus omega and it's integrated over, right. 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 So omega prime is integrated over, and similarly you can do it for the similarly you can do it for the imaginary part, where this one inside is real, because this one inside is inside whatever this thing is real. Therefore, this just becomes plus of itself, right? So both the thing, you just become plus of itself, the minus things. Okay, so right. I'm sorry. I think I have also messed up a little bit here. Let me see. So there's a imaginary part which is this. So if the imaginary part is this, then for minus, omega minus, this, there should be a omega minus here, right? So sorry, what I mean here is perhaps a minus here and a minus here. Okay, if I do that, then I can take the two things, then I can take the minus signs out and convert this into a plus and this into a plus, both of this into a plus. And if I do that, then basically omega cancels and I'm left with 2 omega prime. Okay, then this is correct. And now here also, when I do the change, then I will have a so there's a minus omega, and that minus and this is minus, so this is plus. This is minus, and this one is plus. So I bring the minus signs out. So if I bring the minus signs out, then this becomes minus, and everything here becomes plus. And if this becomes plus, then I see the omega cancels. Now, then basically omega prime cancels, and I'm omega. So this is omega prime plus omega, and minus omega prime plus omega. So this is the 2 omega, and that 2 omega is has come outside. So this is also right. Okay, so that's how you manipulate, and these are the two relations which are very important. These are called Kramers-Kronig relations, and it's basically, it's very universal. This idea is so universal that you can have any response function. If you impose causality conditions on it, for a response function, then it must follow a Kramers-Kronig like relation like this, that its real and imaginary parts become related to each other. Okay. So that's something which is very much very interesting, and it helps a lot in calculations. Like when you try to do various applications of this idea, then this Kramers-Kronig relation is very, very crucial and a very important result. Okay, so so finally, let me end with a interesting topic, which is this idea of scattering. Okay. And let us end with the note that with this question, answering the question, why the sky is blue. Okay, so let's try to do that. So essentially, this is a very basic idea which you have essentially tried to understand this while doing radiation. So let's say there's a charged particle like this, and let's say there's some radiation which is incident on it. When a radiation is incident on it, it starts dancing, right? And it starts dancing as or oscillating because of the electric field here, for instance, in the radiation, because of the electric field, which is considerably strong, depending on what the intensity is, it starts dancing, and when it starts dancing, then it's a oscillating charge. Then that itself sends out radiation. So effectively what happens is electromagnetic wave falls on a charge, and that sends out radiation in all directions. So this process is called scattering. Okay, scattering of light through particles that are present in matter. You can view through matter particles. Light is scattered in this way. That electromagnetic radiation is falling. It's making the charges oscillate, and therefore that is radiating again, and therefore scattering. Okay, so with this idea, there are two kinds of scattering that one can consider. The first one is Thomson scattering, where essentially you consider these particles to be like free charges. Okay, so if the free charges are oscillating, okay, then what you get is called Thomson scattering. And in this case, it's very simple. Like you can take the model as let's say the charge which is oscillating, that is accelerating. M times its acceleration is q times E. This E is the electric field in the radiation. Okay, it's the electric field in the radiation, and now you can just plug it in here and try to solve the equation, which is essentially this oscillation, this kind of a dipole oscillation. So the dipole moment is q times x for the charge, because it's a charged particle, and therefore the this dipole moment again is basically proportional to this whatever direction the electric field is pointing in. So it's oscillating in that direction. So it's making the charge also oscillate in that direction. And therefore, this thing is the dipole, and as you can see, it is also time dependent with the same frequency as the frequency of the incident radiation. This omega is the frequency of the incident radiation, and so if you have an oscillating dipole, it will perform a dipole radiation, and as you know that the total power radiated in that dipole radiation is basically the second time derivative of the dipole moment, mod of that square. So the second time derivative gives me this omega to the 4. And this was the formula that we found, earlier. And this is this comes from the magnitude of the dipole. That square is also there. Okay, so this is the total power emitted, total average power. This averaging has been performed over time. So there's a sine square thing here. So there's a total averaging that has been performed over time. Okay, so here there's one important assumption that I'm making. Again, I'm assuming that this part, although it's a function of x, it's constant over the region where the charge is oscillating. Okay, so that tells me that this amplitude of motion, is basically less than the this is true. I can assume that this is constant, and this doesn't affect my argument here. It just remains as a little bit of a phase here. Okay, maybe you can put in a phase here if you want. Okay, it remains as a phase. This part remains as a phase, constant phase, as long as the wavelength is large compared to the oscillation amplitude. Okay, so this is the wavelength which is large compared to the oscillation amplitude, and this k, if you write as c by omega, then you can write it in this way. And if you write it in this way, you realize that this is nothing but, looking at this expression, QE by MC, it's the magnitude of the maximum velocity. It's the magnitude of the maximum velocity that can be reached. Okay, of course there will be a sine, this thing here, sine omega t here. So maybe, because of this, I can maybe, put in a little bit of a plus phi here, that phase which keeps track of this thing, if the electric field. This phi is supposed to be this kx, whatever that is, and that, I'm assuming is constant throughout the amplitude of motion. Okay. So, right. So, right. So, now this is the total power that is emitted during Thomson scattering. I'm assuming that this is a free charge which is oscillating, and if this is the total power which is being emitted, as you can see that this amplitude goes as 1 over omega squared, and because this is 1 over omega squared, when you write down p squared here, there's a 1 over omega to the power 4, which cancels the omega to the power 4 that comes from the double time derivative. Okay, and therefore this particular cancellation is basically the fact that this total power is independent of the frequency for Thomson scattering. It's a very important result for if you have free charge oscillating and scattering with like light, then it will not depend on frequency at all. Okay, so Thomson scattering, no frequency dependence. It's a very important result. Okay, so good. And now you can define something called cross section in the following way. So this was the emitted radiation, power emitted radiation. So now you can take the Poynting vector of the incident radiation. Okay, if we take the incident, this incident radiation, this one, if I now find the Poynting vector corresponding to that and find the magnitude of the Poynting vector, okay, so if this is the magnitude, this is the magnitude of the Poynting vector, and if I find the magnitude of the Poynting vector and do a time averaging, then I get 2 e squared, e naught squared by 2 mu, 2 mu naught. This 2 comes from the time averaging. Okay, and so now I can define a cross section, scattering's cross section, in the following way: that I take the total power emitted, and divide it by this average Poynting vector, magnitude, which is basically the average energy incident per unit time per unit area along the direction of propagation of the incident wave. Okay, so it's the amount of energy that is incident per unit time per unit area. Okay, and part of that is being like oscillating the charge, and that is being scattered. Okay, in various directions. Okay, so that therefore, if you like, this is like energy per unit time, average energy per unit time. That's the power emitted in all directions, total power that is emitted. And this is the energy per unit time per unit area that is being incident. So this ratio has the dimension of area. Okay, and that is therefore this so-called scattering cross section is basically a cross section area. So it kind of tells us that what is the cross section of the charged particle, or what is the area of the charged particle that this radiation is seeing roughly, and that the incoming radiation is seeing. And that is basically a good measure of the extent to which the scattering is taking place. Okay. Again, this scattering cross section is independent of the frequency here. So I mean, as I said, this is a good measure of the, as you can see, this is a good measure of the energy that is taken from the incident wave, and it's like emitted to in the form of radiation along all directions. So this is a good measure of the effectiveness up to with which the scattering is taking place. Okay. So similarly, there's a very different thing and very more important thing. So here, as you can see, for Thomson scattering, there's no frequency dependence here, right? But now, if instead of free charges, if scattering happens from bound charges, the kind of thing that we just studied for bound charges inside matter, So let's say, there's some dielectric and, there's some electromagnetic radiation, which is being scattered out of the dielectric. Okay. So in that case, we will see that, in that case, we will see that in that case, we will see, the phenomenon is very different. Okay, the phenomenon is very different. So basically, for Rayleigh scattering, this is a different kind of scattering. For that Rayleigh scattering, the bound charges, they oscillate and they give out radiation. Okay, so as we know that the polarization in the bound charges, or the dipole moment that is produced in the bound charges, in our simplistic model at least, it's proportional to the electric field, and this is the polarizability. And we saw in our simplistic model of the, and this electric field is the electric field of the incoming radiation, so it's oscillating. Okay, so in our, with a simple model, we saw that that alpha for this case where the electric field is oscillating, this response of the extent to which the dipole moment is created of the atoms, that is given by this expression. This we just saw a while ago, and if that is given by this expression, then if that is given by this expression, then here omega naught again is this natural frequency given in terms of the atomic parameters. Okay. And here, of course, this is all complex and all, but we can say that in the regime where this omega, this term is the dominant term, okay, then we can actually ignore, these kind of complex, dependencies. This can be ignored because they're just very small compared to this term, okay. And, of course, they have their own effects, the kind of effects that we discussed. But under this approximation, where omega naught is very large compared to omega, then we can, that is also, this is also seen in some sense in several this thing. If this thing is true, and if these scales are negligible, then we can just have alpha, which is given by q square by omega naught square m. There is no omega dependence in alpha anymore. Okay. So although it is a time dependent situation, but time dependent electric field, but if that frequency is very small compared to the natural frequency of the atoms, okay, in that case, which is again the case in many cases, this is the case, the incident radiation, let's say in visible range, it's incident on some kind of dielectric. Then you will see that this is the case, that there's a omega which is small compared to the omega naught, and in that under that assumption we can essentially approximate the alpha as being independent of omega. Okay, under that assumption. So if it is independent of omega, then I mean, this is essentially the limit where omega naught is the smallest scale in the problem, and it's so small that this omega is the smallest scale in the problem, and it's so small that it can be neglected. Okay, so I mean, of course, the oscillation is there. Otherwise, there won't be any effect. I mean, that wherever it produces the physical effect, it's there. But as far as this number is concerned, we can just say that it is a constant. Okay, more or less. So if it is a constant, then we can take this and take the dipole moment. Write the dipole moment in this way, that it's alpha times E. So it's the same thing. Okay, alpha is this thing. Okay. But this alpha doesn't depend on omega anymore. Okay. Earlier we saw for Thomson scattering, this P, this Thomson scattering this P had a dependence on omega, but because of this particular assumption that we are making for Rayleigh scattering, okay, for the bound charges, there is no dependence on omega. Okay. If the charge were free, then there was no effect like this. This omega naught is the natural frequency of the atom. So this omega naught, unless you are talking about bound charges, we cannot talk about this effect at all. Okay, there is no natural frequency otherwise. Okay, then this 1 by omega square, that would be the dominant term in that case. Okay, so but because we are talking about bound charges, this omega naught comes in, and because this omega naught comes in for small enough, this omega, then alpha can be approximated in this way. Okay, Very good. So if alpha is approximated in this way, now we can find the total power. But for now, because this does not depend on omega anymore, it depends on omega naught. Therefore, it's the natural frequency of the atom. Okay, atomic polarization is that thing. So therefore, the total power radiated would be proportional to the fourth power of frequency here, where fourth power of omega here, where this thing comes from the double time derivative of the dipole moment. Okay. So the double time derivative gives me a omega square, and the square here gives me a omega to the 4. Okay, if you remember your radiation formulas. Okay, then this omega to the power 4 is very important, and this is the thing that distinguishes Rayleigh scattering from Thomson scattering. In case of Thomson scattering, the total power didn't have a omega dependence at all, but in case of Rayleigh scattering, the total power does depend on omega to the power 4. And so, if I take this and write it out properly, so it's the ratio omega by omega naught to the power 4, which plays a role here. Again, here it is true that, I'm assuming omega to be small, so this number is small, but this is the leading order effect. I mean, if you say that this is 0, then there is nothing, but, this is small, this is the leading order effect. Okay, omega to the power 4. Okay, so now again you can do the same thing. You can find the average magnitude of the Poynting vector. You can find the average magnitude of the Poynting vector that is given by the same thing as in Thomson scattering. It's the same incident radiation, let's say. It's the same incident radiation. And then you can find the Rayleigh scattering cross section. And you see the Rayleigh scattering cross section is because of the reason that I told you right now, is proportional to omega to the power 4. Okay. So this means that that higher frequencies or shorter wavelengths, they scatter more, because it's a function of omega to the power 4, and therefore blue light scatters more than red light, and this explains why essentially the sky appears bluish. Okay, so this essentially has a very interesting physical applications. Everywhere where you see this classical Rayleigh scattering, we see that there is a frequency dependence when there is a Rayleigh scattering, and this is precisely the reason why omega to the power 4. This is precisely the reason why the sky appears blue. Okay, so this is something which we all must know. Probably you guys already know this and you have seen this before. But I just wanted to connect with the kind of things that we did. We did radiation, so we now know how to find oscillating radiation coming out of oscillating dipoles, and also now we understand what are bound charges compared to free charges. Okay, because I have discussed a little bit of matter with you, and therefore you can distinguish between Thomson scattering and Rayleigh scattering. And of course, there's a quantum scattering as well. I mean, again, that will do you can consider a photon, which is the quanta of this thing, that being scattered from some particle, that you will do in your, probably you have already done it in your quantum mechanics course. But this is because, we are talking about classical phenomenon here. As far as classical electromagnetic waves, scattering of classical electromagnetic waves is concerned in a classical fashion. These are the two processes that can happen, the Thomson scattering and the Rayleigh scattering. And crucially, they differ in the way that Rayleigh scattering is dependent on frequency, while Thomson scattering is not. And this dependence on frequency of Rayleigh scattering explains, why the sky is blue, essentially. Okay, so with that, I will finish this lecture, and so basically, this is probably the last pre-recorded lecture of this course. And okay, so let me terminate here. Thanks a lot for your attention.